The following message is best viewed on an oscilloscope.
Hello, Heikki. Are you there?
Yes.
Hi. Do you want to start sharing your screen, please?
All right.
Good.
Yes. Can you see my slides now?
Yes. Everything is fine. If you want to put your video, if not, that's fine. No problem.
Yeah, I will. Just a second. Something weird happened, but let me do this first, and now share the screen again.
It's fine.
Right. Now it looks good.
Now it's fine. Okay. So, hello everybody. We are starting the second heavy ion session for this international conference for high energy physics. Very interesting program, and we will have in this first part of the session 5 talks already. 1, 2, 3, 4, 5, 6 talks, starting with Heikki Mantisari. So if you want to start, please. He will talk about heavy electron ion collision at the LHEC at FCCEH. Okay.
Thanks for this opportunity to discuss EA collisions in these future facilities on behalf of the LHEC study group collaboration. So my motivation, or our motivation, to study EA collisions at LHEC or FCC in the electron nucleus mode is to study QCD, or in general quantum field theory, in the extremely nonlinear regime. So in this called QCD phase diagram, so-called, we want to explore the region where we are at small enough x to have large gluon densities, basically, and still access this region at high enough scales where weak coupling methods are possible. And this is an interesting region because QCD evolution becomes nonlinear, and we expect to see some genuine nonlinear dynamics. Now, LHEC and FCC provide large center of mass energy, which of course allows small Bjorken X values or kinematical access to small Bjorken X. And the advantage of using nuclei is that parton densities are, of course, enhanced by roughly 81/3 in heavy nuclei, and as such, we can expect some significant enhancement for the gluon densities and for all the nonlinear dynamics when we replace protons by heavy nuclei. Now, in this talk, I'm not really going through the LHEC or FCC projects. We have a separate talk for that, but I'm concentrating on some aspects of the EA physics program of these machines or facilities. So as I said, there is a large center of mass energy, which of course means a huge kinematical coverage. So on the plot, on the left-hand side plot, these say the blue region is the LHEC kinematical coverage, and then FCCE8 would also would even expand that by say an order of magnitude or so. This kinematical coverage should be compared to the rough estimate of the saturation scale of the lead nucleus, illustrated by the gray band here. So this is roughly the scale where we expect nonlinear dynamics to be important or to have large effect on the physics, and we want to be able to access this region and then smaller Birkenecks or higher densities in the region where this scale is in the perturbative region in order to allow also in order to make perturbative methods applicable. This red, I should also mention that there is an electron-ion collider project moving forward rapidly in the US. This EIC project will have a significantly smaller kinematical coverage due to the smaller center of mass energy that's illustrated by the red area here. And then all these kinematical domains should be compared to what we currently have for nuclear DIS, and which is only this tiny part of the phase space shown here, labeled as present DIS data. So there is a huge kinematical phase space yet that needs to be explored in the future facilities. So as I said, I want to go through some of the major parts of the EA program. In particular, in this talk, I discuss partonic structure of nuclei, exclusive vector meson production, a little bit about diffractive structure functions, and some genuine nonlinear QCD dynamics. All this and much more is covered in detail in the LHEC or FCC conceptual design report, for which an update will be, which is basically a completely new document. This updated document should be available in archive hopefully tomorrow. So to study nuclear structure at high energies, it's a fundamentally interesting physics. For example, when we are looking for the constituents of the partonic constituents of the nucleus or nonlinear evolution. And also this fundamentally interesting physics has some applications to, for example, quark-gluon plasma studies and other studies that we are currently and in the future doing at the LHC, for example, in lead-lead collisions. Okay, so let's start with nuclear PDFs. So thanks to Hera, we know very precisely the partonic structure for protons down to pretty small, like say 10 to the -4, or even maybe a little bit smaller, depends on how you define, so we say good knowledge, or when the uncertainties start to then blow up basically when you go to X smaller than that. But then for nuclei, because there is no nuclear DIS collider, there's no EA collider up to date, then there is very little data that can be used in the determination of nuclear parton distribution functions. So the plot down here on the right shows basically the XQ² region from which one can include data to the global analysis of nuclear PDFs, for in this example on the so-called EPPS-16 nuclear PDF, which is the current state of the art. And only a basically small part of this phase space, mostly focusing on large X, it can be currently included because, as I said, there is no small X nuclear DIS data due to the fact that, say, LHEC is not available yet. And consequently, then the partonic structure of nuclei at small x's, that has a pretty large uncertainties. Now, the best observable to use to determine nuclear PDFs is the measurement of structure functions, F2 and FL. This can be done over a wide kinematical domain very precisely in these future facilities, LHEC and FCC, even in case of heavy quarks. So I'm here showing some pseudo data on the left-hand side for F2 charm, on the right-hand side for F2 bottom. The uncertainties are very small, even in case of B quark production, and the kinematical coverage is as you can see, is quite broad. Then you can ask, what is the implication of these or impact of these measurements for nuclear PDFs? But okay, before I show the impact, I can also show what's the expected precision for extracting nuclear effects. So this in this plot, I'm showing the X dependence of the nuclear suppression factor. So basically, in the absence of nuclear effects, this lead to proton ratio is just 1. So this ratio is shown at different Q² pins as a function of X. And you can see that the pseudo data has basically very almost negligible uncertainties. And this is generated by assuming the nuclear effects as included in the EPPS16 nuclear parton distribution functions. So these precise measurements can be expected to have a significant effect on the nuclear PDF determination. What is shown here is the impact of the LHEC data or pseudo data on the global analysis that results in the nuclear modification factors for different parton distributions. So what is shown here is the nuclear modification for the gluon distribution in the nucleon, in the anucleon at initial scale. And this is the so-called EPPS16 star parameterization for nuclear PDF, which is very flexible parameterization, and that flexibility basically means that uncertainties explode in the region where there is no data constraining the PDFs. And the current situation is shown on the left-hand side. So basically, because we only have high X data available, then at low X we have basically no idea if you really take seriously this kind of analysis. Then if we include the inclusive structure function measurements from LHEC to the global analysis, the uncertainty bands shrink quite a lot, as you can see on the middle panel here. And then actually the charm production is very powerful, or is very powerful in constraining the nuclear PDFs, because then if we also include the charm production in this kind of exercise, then the resulting nuclear modification for the gluon PDF becomes quite precisely determined down to X, say 10 to -4 or so. I should also emphasize that also some LHC-PA data already enters here, but that is basically at such a high scales that it doesn't have such a huge impact on the PDF determination. Also, PA collisions are of course much more, well, let's say less clean, and as such, it's not possible to obtain precision at the level of DIX experiments. The other approach to determine nuclear PDFs is not to perform a global analysis, but just rely on or take the advantage of the fact that the wide kinematical coverage of the LHEC already provides us enough data so that we can basically just fit PDFs to the LHEC structure function data without really requiring a global analysis to multiple measurements as done in the EPPS16 analysis. So what is shown on the left is the relative uncertainty of the gluon PDF at 10 GeV² scale. And then on the top panel shows the proton case. So what we get by just fitting fitting proton PDF to the LHEC pseudodata. And then let's focus on the middle panel, which shows the relative uncertainty of the gluon in the lead nucleus. The red panel is the result of after including the LHEC pseudodata, and then we can see that let's say in case of LHEC, the uncertainties reach 10% at say 2 × 10⁻⁵, x 2 × 10⁻⁵ or so. So a very good precision is obtained down to such a low Bjorken X. And then the black region includes also the FCC pseudodata, and in that case, the uncertainties start to explode at significantly smaller X still, let's say even below 10⁻⁵. The lower panel here shows the nucleus to proton ratio basically for the gluon PDF and relative uncertainty to that. And then you can compare these LHEC or FCC results to the current EPPS 16 uncertainty, which is let's say at x 10⁻⁴ or so. There is a dramatic improvement from some pretty large uncertainty to basically almost 0 uncertainty. In addition to determining PDFs, then this makes also possible to perform precision tests for collinear factorization with nuclear targets. Okay, let me then move on to diffraction, which is interesting because because by diffraction I mean scattering with no net color charge transfer. So at leading order, one needs to exchange at least 2 gluons, and consequently the cross section is roughly proportional to the gluon density squared, although in reality it's more complex or complicated. And as such, these diffractive processes are very sensitive probes to the partonic structure at small x. And exclusive vector meson production, where we produce exactly 1 particle, is particularly interesting because there is an advantage that the total momentum transfer T can be measured, and that is by definition Fourier conjugate to impact parameter. So then it's also possible to do some spatial imaging. Here, a demonstration of the sensitivity to the nuclear effects is shown by calculating the exclusive shape psi production as a function of center of mass energy in EP and E lead collisions. On the left this is at low virtualities, and on the right at high virtualities. And the normalization is such that in the absence of nuclear effects, these 2 curves would collapse. So the scaling is A squared here. And as you can see, then the nuclear modification to the exclusive shape psi production is dramatic. It's a huge effect, much larger than what we expect to see in, say, structure function measurements. Then if you measure the cross section as a function of momentum transfer, then as I mentioned, it's possible to probe the spatial distribution of partons in the heavy nucleus. Then these vector meson production, or in general diffractive cross sections, are divided in 2 categories. We can look at what I call coherent diffraction, where the lead target remains intact. And if I take that has this genuine or well-known diffractive pattern shown here. So we have some diffractive minima. And if I take such a cross section measured as a function of momentum transfer squared, and I do the Fourier transform, what I get is the spatial distribution of small x gluons in the nucleus. Then I can look at incoherent cross section, in which there is again no color charge transferred, but the target breaks up, and it can be shown that such a process is sensitive to the event-by-event fluctuations of the scattering amplitude. Not going into details here, but that basically the difference between the solid and dashed line is the effect of potential nucleon shape fluctuations in the nucleus. And then thanks to the large kinematical phase space in the LHEC or FCC, we could study how the fluctuating substructure of nucleons evolves as a function of Bjorken X. Then, in addition to single particle production, diffractive single particle production, one can do inclusive diffraction, basically measuring particle production or production of a system of particles with given invariant mass, still requiring no color charge transfer. And then these processes can be expressed theoretically in terms of diffractive.
2 minutes left. Sorry.
In terms of diffractive PDFs that have never been measured for nuclei. So this is completely new measurement that can be done, and then that can be used to really somehow such measurements provide very strong model constraints for some models describing basically the interaction of say photon or quark anti-quark dipole with the strong color field of the nucleus. So finally, for the last minutes, I want to say a few words about the nonlinear QCD. Already the nuclear suppression factors or nuclear effects that I mentioned in case of inclusive and exclusive scattering, those can be seen to be results of nonlinear QCD dynamics, but one can also use other approaches like collinear factorization and nuclear PDFs to describe, say, suppression of F2, for example. But with the high precision and wide kinematical coverage in the LHEC, we can have a detailed physics program including many simultaneous description of multiple processes to accurately determine whether nonlinear QCD is taking place. Nonlinear QCD evolution is visible in these future experiments. This is one on the left. Here I'm showing just one saturation model calculation of the nuclear suppression factor for the F2 structure function ratio. So you can see the kind of smooth transition from the very nonlinear, highly nonlinear region down here on the left to the dilute region on the right, where densities get so much or get smaller and nonlinear effects die out. Now, if one tries to do, for example, D-club evolve PDF fits to structure function data, then if the saturation effect, nonlinear saturation effects are having a significant effect in the, say, LHEC kinematics, then one should expect to see at least some tensions or even failures of the D-club fits in the description of the future structure function data. But what is probably more effective is to look for more differential measurements when we want to look for genuine nonlinear QCD evolution effects. For example, here I'm showing the azimuthal correlation of two hadrons in inclusive dihadron production in DIS. And the idea is to look for back-to-back correlation. So if the solid black line here is the calculation for the back-to-back correlations in electron-proton collisions. Now, of course, at leading order, you expect the two particles to be back-to-back, and then higher order effects give you some distribution around pi here. Now, if you are in the saturated region, then the gluons are carrying transverse momentum, which is of the order of the so-called saturation scale, which increases when you go to heavy nuclei and increases when you go to smaller X. So you expect that when this Q scale grows, so when you go to larger nuclei or smaller X, then because the intrinsic transverse momentum grows, you expect this back-to-back peak to be washed out. And then this is illustrated in this calculation here. So when I go to smaller x in the proton case, so go from the solid black line to this dashed red line by going to roughly 2 to 3 times higher center of mass energy, then this back peak is getting slightly smaller. But yeah.
Sorry, can you please conclude? Sorry.
Yeah, I'm basically done. So when I go to nuclear case, then it's basically almost flat distribution. So the nucleus becomes very powerful, or there's a clear nuclear enhancement of the nonlinear effects. So basically, that brings me to my summary slide that I don't need to read to you. I just flash the other LHEC talks here, and thank you for attention.
Thank you very much, Heikki. We have almost no time for questions, only very urgent one. If somebody wants to ask a quick question, please.
Federico Antinori here. Can you hear me?
Yes, please.
Hi. So yeah, very, very nice talk. I just wanted to make a small rectification, rather a comment on the physics reach at the LHC. If you can go to slide 2, where you have the comparison of the different machines and measurements with proton lead at the LHC. That is where you are with measurements in the central barrels. But if you take, for instance, the focal, which is being proposed for the ALICE experiment, there you get down to a few 10 to the minus 6 at a Q square of 10. So it's significantly lower. Okay,
I completely agree. This P-LED region, LHC P-LED region, I think this refers to like W and C production, but doesn't really reflect the full potential of LHC.
Okay, that was it. Just
Thank you very much, Federico. So thank you very much, Heikki. Now we please stop sharing. Thank you. And now we go to Mikhail.
Hi, do you hear me?
Yes.
Okay, I will start to share my camera and share my presentation. Is it working?
Yes, it is.
Well,
please go ahead.
Okay. So hello, good afternoon. So my name is Michal Krylina, and first of all, I would like to thank to organizers for this opportunity. So I'm going to, let's say, continue in specific part what Heikki spoke about electron-ion colliders, and specifically about nuclear shadowing, how we can calculate, and what about we should be careful, especially at lower energies with EIC. So let's start. There is some outline. So first of all, I will speak a little bit more about theory, specifically about color dipole formalism. And then I will show you some results, and I will show you how individual effects have effect for the final results. Then I would like to open a small discussion about the centralities in electron-ion colliders. And then, of course, the result of this work are basically universal and can be applied for basically all processes involving nuclear target. Okay, so let's start with color dipole framework. Color dipole framework, it's, I would say, ideal theoretical or phenomenological framework for studying nuclear collisions. It's formulated in the rest frame of the nucleus. So usually you have the target nucleus and you have some incoming projectile. In our case of electron-ion colliders, it's some electron, of course, but then we have some virtual photons. And in the focal expansion, we can expand this virtual photon in different, let's say, hadron states. Or of course, there is some bare photon, but that doesn't interact. So I skip it to the first interacting Fock component. It's QQ bar. Then, of course, we have higher QQ bar, 1 gluon, 2 gluons, or 3 gluons. Okay, basically, first I will care about the proton target. In such case, we usually care about only the first Fock component for QQ bar, because every this Fock component has different lifetime, and the smallest is the lightest. So usually the lifetime is the long, and assuming the small size of the proton target is the highest chance of interaction in comparison with the higher Fock component is heavier, the life is shorter, so the chance of interaction with proton is smaller. But it's starting to be interesting in the nuclear target, but about that later. So within a color dipole formalism, the total cross section is quite simple. It's basically, let's say, something like convolution of the wave function. The wave function is here. It's basically a description of the splitting of the virtual photon in QQ bar pair that can be basically derived from QED, and it's convoluted with the dipole cross section. This dipole cross section usually has some form of the phenomenological model fitted from EP-DIS data. So this is, as you will see later, it's the main source of the uncertainty using this formalism. But in comparison, for example, with the perturbative QCD, the advantage of the color dipole framework is that you can go, for example, for very small virtualities, very small Q square, because all those non-perturbative effects actually are hidden in this dipole cross section. So we can afford to go, let's say, in a little bit even more different and kinematic than with using the standard perturbative methods. Okay, here our first improvement in our calculation is that, as I said, the QQ bar couple exists quite long time because it's quite light. So, but still are for each other they are color object and they can exchange some gluons. Of course, we are completely in perturbative, non-perturbative region. So, so the description is phenomenological, but there it's a small correction. Okay. So that will be the proton target. If we go to the nuclear target, here the situation is more complex, and because we sit in the rest frame of the nuclear target, so basically we do like calculation of the incoming quark-antiquark couple pair fluctuation, how do you want to call it, with the individual nucleons inside the nucleus. So as I said, we have like a lifetime of this fluctuation, or more correctly, we call it coherence length or coherence time. It's actual time how long this Fock state exists. Basically, there is a full expression for this QQ bar component. Simply said, roughly it's 1/2 nucleon mass x Bjorken. So smaller x we go, the longer coherence length is, and there is a probability there will be some interaction. Okay, so basically, if we have enough long coherence length, I mean that this coherent length is much higher than the nuclear radius. So naively, we can imagine like this QQ bar is created long before the hitting nucleus, and will be destroyed long behind the nucleus. So it's like interact coherently with the whole nucleus. In that case, we can the dipole cross section described by this aconal approximation. It's basically the Glauber-Gribov formula. So in that case, such approximation is quite simple. The calculations are quite simple, and for example, in case of LHC energy, it's safe to use. But okay, but let's assume this situation when x Bjorken x is not so small, it's quite large. Let's say 10 to minus 2. The coherence length is not necessary fulfill this condition, and in that case we would overestimate the nuclear shadowing or suppression. So for that case, you can apply the so-called green function technique. The green function technique is technique basically known from quantum mechanics. Feynman used it for the formulation of quantum field theory. Practically, it's about the two-dimensional Schrödinger equation. And this green function described treat the coherence length like exactly. And the importance of this green function technique increase with the higher component, because as I said, the coherence length is shorter. So therefore, with higher and higher state, Fock state, you less and less fulfill this condition, and therefore you have to you should use some green technique. In this picture, you can see actually the dashed line is the using the calculation using by simply aconal approximation, whereas the solid line is green function technique. So you can see at very small x, they give the same result, but they differ for going to larger x, what one should expect. Okay, so that is just a small sketch about the how to imagine green function and what actually is doing. So basically, you can imagine that photon goes in QQ bar. This pair can propagate through the different paths through the nucleus, that where the radial distance between them vary, and so on. So all this is incorporated in the gluon in this green function. Okay, so far I spoke only about the QQ bar Fock component, and if you assume only this lowest Fock component, we speak about the about quark shadowing. If we added the if we take the higher Fock state, for example, with one gluon or even more gluons, we speak about the gluon shadowing. For example, here is the sketch. Again, the formalism by using green, because as I said previously, for higher components, Fock components with more elements, we are more motivated to use the green function technique. So, but the principle is the same. Okay. However, you can imagine, for example, even only the wave function virtual photon go to QQ bar plus radiated gluon from one of those quarks is quite difficult. So in case of enough high Q square, let's say 1 to 2 to 4 GeV, it's very safe to use approximation where for such enough large virtuality, the QQ bar is enough close each other, so we can consider as the gluon. So effectively, we can this wave function that is I return here. This we can replace by effective wave function virtual photon to gluon. So it's one approximation. The other approximation is for the dipole cross section, because if you consider only small size, for example, here is a R. In that case, the property of the dipole cross section is that you can safely describe it by square form, and only question is how to determine this factor C. Okay, there are basically various ways how to get it. One I discuss here, or I will show you in the figures, is I call it C0. It denotes the derivative of the dipole cross section for R square goes to 0, and a more realistic C effective that's coming from the long coherence length limit condition. And okay. Other question here is exact formula. How is the mass of the second lowest Fock component? As you can see, it depends of alpha g. Alpha g is denotes the fraction of the momentum that is taken by gluon. If we take this fraction quite large, let's say half of the momentum, then the mass of QQ bar and QQ bar gluon is comparable. But the most common case is when the alpha G is small. In such a case, this mass is much higher, and therefore we need to use the green function technique. But at the end, so you can calculate this gluon shadowing separately using only the QQ bar gluon case. And you can calculate something like nuclear modification factor only for this gluon. And in the final calculations, I mean, here, you can implement it by multiplication of the dipole cross section that is actually appropriate to the gluon distribution. So you simply multiply, and effectively it also includes some interference terms. Okay, there is one note about the Balitsky-Kolchegov equation, because someone can say, but I can consider the higher Fock state using the Balitsky-Kolchegov equation, because in our case we calculate every higher Fock state separately, and it's pretty difficult, especially with the higher components. So basically it's true. However, disadvantage of the BK evolution equation is that they consider the coherence length of all higher Fock components like it's enough big, it's enough long coherence length. So they use the Eikonal form for the dipole cross section or amplitude to be correctly, and that can lead to overestimating of the nuclear shadowing. Yes.
You have 5 minutes left.
Okay, sure. Yes. Okay, so so that was a short comment about the Balitsky-Kolchegov equation. So there are some results. This is for calcium for different scales. So here you can see for different lines, every different line corresponds to different dipole cross section. So you can see that is the main source of the main source of the uncertainty using this formulation. So this was simply for quark shadowing. This is the same, but for the lead. So basically, it's a higher suppression. Okay, so there are results only for the gluon shadowing alone. So it's the factor RG. Here again, the different colors correspond to different dipole cross sections, and the solid and dashed lines correspond to different approach to calculation the C factor. So at the end, this C0 and C effective, for example, here the green dash and green solid, they define some uncertainty coming from my gluon shadowing estimation. So at the end, if you put all together, so here again the lines are only quark shadowing, and these areas, for example, here the red is the final calculation for individual dipole cross sections, and the area, the color area, correspond to uncertainty coming from gluon shadowing. So, but basically, for example, here also for lead. So basically, you can see there are quite large difference using there are different results for different dipole cross sections. So hopefully, at EIC or LHEC in the future, we will be able to say, okay, this parameterization doesn't work so good. And here is comparison also the black line, the solid and dashed line that correspond to EPPS or NCTEC. But of course, it's difficult for them because they are basically they are based on some experimental data, but we don't have really reliable data for very small Bjork and X. One of the best so far are, for example, these data from EMC and E665. But as you can see, the error is quite large to say, okay, which dipole cross section is better or worse, and even it's not for constant Q square factor. Okay, so basically dipole formalism allows more, not only F2 structure but we can theoretically can calculate the centrality dependence, longitudinal structure function, or structure function on a C quark or B quark. All is possible, and actually we provided some predictions for EIC Monte Carlo events. So there is, for example, one example for the centrality for LED and different scale, where the dashed line is the minimum bias, and the rest is for different centrality classes. But this is calculated, I would say, theoretically, because I do like in the ratio of the in comparison to total cross section. But of course, this approach cannot be applied in the experimental way, and moreover, usually, of course, because it's electron nucleus, we cannot use the standard Glauber theory for the calculation about how many participants and so on. So there are like one paper and some presentations on this topic. So, but I think it's quite open topic, and it will be good to find some agreement between experimentalists and theorists how to calculate that, because when I spoke with some people, maybe they could be able to measure the centrality at EIC or in the future at LHEC. That of course can give us more accurate physics. Okay, so generally these approaches of using the green function or other approach to gluon shadowing is universal. You can use for all energy, especially at lower energies, where you have problem with the enough long coherence length. For example, for RIG or EIC, or let's say some extreme kinematic at LHC, like extremely large rapidities. So, for example, I would call it hot topic is, for example, for nuclear vector meson photo or electroproduction, DVCS, dijets at EIC, or ultraperipheral collisions. So there is like very fast preliminary. Here you can see for RIG that the dashed line is without correction. This is only long coherence length limit, and the solid lines is using the finite coherence length correction, and the difference on the large rapidity is coming from gluon shadowing. The same is for LHC, but it's only for really extreme rapidities, and gluon shadowing starting to be more interesting for mid rapidity. Okay, so there is some conclusions, and thank you for your attention.
Thank you very much, Michal. Very interesting presentation. And we have some questions. Any raising hand? I don't see any. On Mattermost, no. Okay, if not, thank you again, Michal,
Okay,
and
thank you.
Thanks for your contribution. Thank you. Now we can have the presentation from Inbridge. Soborowski. Hello.
Hello. Can
Yes.
you hear me?
Yes, very well.
Thank you very much. So, so you can see all my screen, yes, now?
Yes, everything is perfect. Now you can start if you want. We have
Thank you.
time.
So, hello. I would like to thank the organizers to give a possibility to present a talk on cell similarity, fractality, and entropy principle in collisions of hadrons and nuclei at RIG, Tevatron, and LHC. The work was done in collaboration with Michael Tokarev from GNR Dubna. After some motivation and goals, I'll mention the principles and symmetries which form the basis of the Z-scaling approach to inclusive reaction. Then I will define the variable Z and its connection to entropy. I'll mention the conservation law of fractal cumulativity and will discuss the quantization of fractal dimensions and fractal cumulativity. Our motivation and goals. We search for new symmetries and conservation laws which govern physics at small scales. Search For signatures of phase transition in nuclear matter exploiting scaling properties in suitable representation of the data. Our goal is to develop a unified approach for the description of particle production reflecting the principle of self-similarity, fractality, and locality of hadron interaction at a constituent level. Principles and symmetries. As stressed by Lederman, fundamental symmetry principles dictate the basic law of physics, control the structure of matter, and define the fundamental forces in nature. According to Emmy Noether, for every conservation law, there must be a continuous symmetry. Principles are reflected as regularities in measurable observables and can be usually expressed as scaling in a suitable representation of data. The Z-scaling of differential cross-section of inclusive particle production is used as a tool to search for and study of principles and symmetries that reflect properties of hadron interactions at constituent level. In our case, these are self-similarity, fractality, and locality. The self-similarity in inclusive reactions. The differential cross-sections for production of inclusive particle depends on reaction characteristics, particle characteristics, structural and dynamical characteristics. The assumption of self-similarity of hadron interactions at the constituent level transfers to requirement of universal description of inclusive spectra by a scaling function C. It should be achieved by grouping some characteristics of the inclusive reaction into a suitable variable Z. We search for a solution that would depend on self-similarity variable Z in a universal way. According to Barenblatt, there are self-similarity of two types. In the first type, the self-similarity variables and functions are constructed via dimensional analysis from dimensional quantities describing the system. Stavinsky studied cumulative particle production and found self-similarity variable and functions in this form. But the universality was broken by power asymptotic at high Z, high PT. According to the self-similarity of the second type, if phi does not converge but has power asymptotic for extreme value of the variables, the self-similar solution of the second time can be expressed via a ratio with some exponent delta E here. According to the hypothesis of self-similarity in relativistic nuclear physics raised by Baldin, the parameters delta E should be found from the experiment. The variable Z is a self-similarity variable of the second time. The exponent delta E are written as you can see here. The variable Z is expressed via momentum fractions, which define a constituent subprocess illustrated in this diagram on the right. Z is a fractal measure. Model parameters are fractal dimensions delta, which describe the structure of the incoming objects, and epsilon, which describe the fragmentation processes in the final state. Omega is a relative number of constituent configurations containing the subprocess defined by the fraction x and y. Omega to minus first is resolution at which the constituent subprocess can be singled out of the inclusive reaction. This is the fractal property of Z. Locality of hadron interaction is expressed via interactions of the constituents. The constituent subprocesses are subject to kinematic constraint with a recoil mass mx. The fractal measure Z is defined as a ratio where Vmax is maximum of the functions written here, where d and d eta is the multiplicity density, C is specific heat, and delta and epsilon are fractal dimensions. The nominator is a transverse kinetic energy consumed in production of the inclusive particle and recoil particle. Vmax means maximum relative number of configurations that can lead to the production of MA and MB. Microscopic features of constituent subprocesses are given in terms of momentum fractions obtained from minimal resolution omega with the kinematic constraints written here. The scaling variable and the scaling functions are subject to scale transformation with a constant W0, which is the absolute number of configurations of the system. These drops out of the scaling, because of scaling. V0 depends on the type of the inclusive particle, so we can define the ratios with respect to pions and the scale transformation with alpha S. This scale transformation preserves the normalization condition. We have shown that scaling functions for different hadrons collapse to a single curve using transformation with suitable values of alpha F. Now I come to the Z-scaling in proton-proton collision at RIC. This slide illustrates Z-scaling of identified hadrons in Pepe collision at RIC. The symbols represents data measured at different energies, angles, and for different inclusive particles. One can see a collapse of data point onto a single curve, provided the scaling parameters are those as shown in figure. One can obtain in such a way the energy and angular independence of the scaling function, its flavor independence, saturation for small z, and a power law at high z. The cell similarity dictates the properties of constituent subprocesses, such as momentum fractions, recall mass, and energy losses by production of the inclusive particle. This is illustrated on strangeness production in proton-proton collisions at 200 GeV. One can see that the more strangeness, the larger momentum fraction of the subprocess. This also, for more strangeness, the larger recall mass in the constituent subprocess. The more strangeness, the larger fragmentation dimension, meaning the larger energy loss by production of the inclusive particles. All three characteristics for baryons are larger than for mesons. Now I come to the Z-scaling at the tevatron and LHC. This slide illustrates cell similarity of top quark production at the tevatron and LHC. The symbols represents data measured by Atlas, CMS, and D0 collaborations in different dilepton, lepton jet, and dijet channels at different energies. One can see a collapse of data point into a single curve, provided the fragmentation dimension for the top quark is 0, meaning that the energy losses by production of the top quark are negligible. Other parameters are the same as for other particles. These confirm the cell similarity of top quark production in Pepe collisions. This slide illustrates cell similarity of jet production at the tevatron and LHC at large transverse momentum and small scales. The jet spectra were measured at different energies and can be represented in the Z-scaling form by a straight line in the log-log plot in this high Z region. This is a new test of the Z-scaling at the LHC, which was asked to study structural phenomena and cell similarity at small scales. I summarize properties of the scaling function in Pepe collisions. These energy independence of CZ, angular independence of CZ, multiplicity independence, saturation at low Z, and power law at high Z. The flavor independent of C means that for pions up to top quark, scaling functions are practically the same. Now I come to the Z-scaling and gold-gold collisions at RIC. This slide illustrates negative hadron production in central and peripheral gold-gold collisions measured by the star collaboration at different energies. The scaling parameters in the gold-gold system are different from those in the Pepe one. There is additivity of the fractal dimensions written here. The increase of fragmentation dimension with multiplicity density means increase of energy loss with multiplicity. And increase with centrality. The small value of specific heat in the gold-gold system means the larger temperature fluctuations in our system than in the Pepe one. Under this assumption, one can see energy and centrality independence of the scaling function C and the power law in low and high Z region. The line represents the scaling in Pepe collisions. The multiplicity dependence of fragmentation dimension transforms to different energy loss for peripheral and central collisions at different energies. Let us consider, for example, production of a negative hadron with 4 GeV. The percentage of energy loss in the peripheral and central collisions at different energies are shown in the left and right column respectively. One can see increase of the energy loss with energy, collision energy, and increase with the centrality. Now I come to the variable Z and entropy. The variable Z is defined in terms of an underlying constituent subprocess. Its connections to the entropy is via the Vmax, which is the maximum number of configurations, which contains the constituent configurations defined by the fractions X and Y. We consider constituent subprocesses that are mutually independent and write the entropy of the remaining part of the system as follows. Where T and the eta characterizes temperature of the produced system, C is the specific heat of the produced medium, delta and epsilon are fractal dimension in the space of the momentum fractions. Maximal entropy corresponds to maximal number of configurations under the kinematic constraints. This gives us omega max and the values of z for every momentum of the inclusive particle. The momentum fractions are obtained from maximum entropy principle under the kinematic constraints, which depends on Lorentz invariance. This corresponds to maximization of the function of C with a Lagrange multiplicator beta. The principle of maximal entropy gives us 4 conditions for 4 unknown fractions x and y. It can be shown exactly that the solution obey this relation, which is conservation law for arbitrary values of momenta and fractions delta and epsilon. The conserved quantity C is proportional to the fractal dimension delta and the respective momentum fraction zeta. The properties of the conserved quantity C. C characterizes property of a fractal-like object or fractal-like process with fractal dimension D to form a structural aggregate with certain degree of local compactness. It characterizes ability of the fractal systems to create structural constituents. C is proportional to the fractal dimension D of a respective fractal system. The larger momentum fraction zeta carries a structural constituent of the fractal-like system, the larger value of C it has. C is named fractal cumulativity of a fractal-like structure with a dimension D, carried by its constituents is the momentum fraction zeta. The conservation of fractal cumulativity can be stated as follows. The fractal cumulativity before interaction is equal to fractal cumulativity after interaction for any binary constituent subprocess. The conservation law does not depend on motion. It depends only on resolution. We assume here that hadron constituents possess fractal structure, fragmentation processes have fractal-like character, and compactness of the fractal systems is governed by the Heisenberg uncertainty principle. There is a composition rules for the quantity C. Define a different momentum fraction zeta. The composition rule leads to exponential type of the distribution with non-extensibility parameter Q depending on the fractal dimensions. The properties of C for fractal with a dimension D is additivity for small c and non-additivity for large c, for large values of c. There exists an analogy between cumulativity and energy. For a fractal-like object, the cumulativity is function of the momentum fraction zeta in a resolution-dependent reference system given by momenta of the colliding and inclusive particles. For point-like objects, energy is function of the velocity fraction beta in a motion-dependent reference system given by a velocity triad. The photon with mass 0 has analogous in non-structural objects with d equals 0. The quantization of energy has its analogous in quantization of fractal dimensions and quantization of fractal cumulativity, which are shown later. There are, however, differences, the main of which is that there is no absolute scale for the momentum fraction zeta, while the velocity fraction has absolute scale. For maximum entropy principle, we obtain constraints from the momentum fractions. Therefore, here they are explicitly written. They depend. The momentum fractions depend on functions k1 and k2, which are functions of the inclusive particle momentum. The system is solved numerically. But at the fractal limit, where the fractal limit is defined by where all fractions are equal to unity, the 4 constraints for the momentum fractions in this region are linearized according to Taylor expansion. This gives us 4 equations in this region for 4 unknown fraction x and y. The overline symbols are calculated at the fractal limit. Expression in red depend on pt. The solution of this can be obtained exactly, and this is a specific functions on momentum on the fractal dimensions delta and epsilon. The solution we plug into the omega and then into the maximal entropy in the fractal limit and obtain entropy near the fractal limit in such a form. There is entropy decomposition as omega, which can be written in this form. The entropy as gamma depends on momenta and masses of the colliding and inclusive particles. Entropy as 0 is a constant. Entropy as gamma depends solely on fractal dimensions, where S gamma can be written as follows. Here is S epsilon. There is a symmetry property of S gamma. The entropy S gamma can be interpreted within a statistical ensemble of interacting fractal configurations, which is a large collection of the interacting fractals with random configurations, but with the same fractal dimensions. The entropy S gamma for a single average fractal configuration of the system can be written as follows. The entropy S gamma for the whole statistical ensemble is additive, and therefore it has the following form. Quantization of fractal dimensions.
5 minutes left.
5 minutes?
You have 5 minutes left.
Yes. The entropy of the quantization of fractal dimensions. The entropy S gamma can be represented by all possible arrangements in which the fractal dimensions of the interacting fractal structures are composed of identical dimensional quanta, each of the size C, provided that the fractal dimensions have the quantum form. Statistical interpretation of the entropy S gamma. The S gamma can be interpreted as the logarithm of a number of different ways, in which identical dimensional quanta can be distributed among the fractal dimensions of the interacting fractal structures. The statistical interpretation of the entropy S gamma is only possible by the quantization of fractal dimensions. The quantization of fractal dimensions is connected with quantum character of fractal cumulativity C. There is a conservation law for the number of quantum of fractal quanta of cumulativity. The number of cumulativity quanta before and after a binary subprocess is the same. The number of quanta of fractal cumulativity is conserved at any resolution given by arbitrary momenta of the colliding and inclusive particles. Now I come to the summary. Z-scaling is a specific feature of high-pete particle production established in proton-antiproton collisions, or proton-proton collisions. It reflects cell similarity, locality, and fractality of hadron interactions at the constituent level. The hypothesis of scaling of cell similarity and fractality was tested in gold-gold collision at RIC using Z-presentation of spectra of negative hadrons. Analysis of star Beslan data indicates approximate energy and multiplicity independence of the scaling function psi. The variable Z depends on multiplicity, heat capacity, and entropy of constituent configuration of the interacting system. The constituent energy loss as a function of energy and centrality of collisions and momentum of inclusive particle was estimated. Summary 2. We have shown that Z-scaling containing the principle of maximal entropy includes conservation of the quantity C, which is named fractal cumulativity. Fractal cumulativity reflects ability of fractal system to create structural constituents. The cumulativity C of a fractal object or fractal-like process is proportional to its fractal dimension and represents a simple function of the momentum fraction zeta. The fractal dimension D is interpreted as quantity which has quantum nature. The quantization of fractal dimension D results in preservation of the number of quanta of cumulativity in binary subprocesses at any resolution. Thank you for your attention.
Thank you very much, English. Very interesting questions. Let's see. We have a question from the participants, not from the chat. Let's see the most. No.
I think we have raised hand, Arturo.
Oh, yes. Yuri, can you please open your microphone?
Yes, yes. So I have a rather general question. I mean, in the first part of the talk or somewhere in the middle, for example, you were introducing this psi function, which is independent of everything and everything scales with the psi. But basically, the general question to all of the talk is, well, what do we learn from that? I mean, can we learn anything about the properties of matter, of processes from this?
We are studying the spectra of identified hadrons and various particles, and we suppose that if there is a phase transition in a system, for example, in nuclear system, there should be a discontinuity of these model parameters, delta or epsilon, and the specific heat. we search for such a discontinuity, we haven't found until now in this negative hadron production. But our assumption is that the self-similarity is a stronger property than than phase transition. It should be preserved by the phase transition from above and from below. But only this parameter should somehow change, have to show abrupt change. This is our idea to search for such a transition.
Okay. Okay, if we don't have any more questions, we thank again Imrich Orowski. Thank you very much, Imrich.
Okay.
So please stop sharing your screen. And now, stop. Okay, good. And your video. Stop your video. Okay, and now we have the contribution from Irais Bautista. Irais?
Hello, can you hear me?
Yes.
Can you see the slide? Sorry, can you see the slides?
Yes, we can see the slides, but you have to put it in full screen. But also like this, it works. You can start if you want.
Okay, so I will present.
Yes. Okay, now it's better. You can go to your first slide if you want.
Yeah. So
okay.
First, I would like to thank the organizers for giving me the opportunity to give this talk. And I will present a study of the effects of initial state fluctuations on our equilibrium phase transition for PP collisions at LHC energies. So to start, in PP collisions at LHC energy, we know that these are small systems and the finite size and fluctuation expense become relevant to these systems. So we also have a fast expansion and cooling with a lifetime of a few Fermi over C. And we will work on the framework of color sources. So in this framework, we will have a transverse impact parameter plane, and then we will have overlap strips that are stretched among the partons of the two projectiles or targets. And then those will increase as the energy of the collision and also as the number of participants. We will characterize these strings with a length, with a transverse area of 20.5 Fermi. This comes from lattice bilocal correlation calculations. And we expect to have a deconfinement when we have the density of these strings that where quarks and gluons become so high, this density that will have an overlap of this strongly. So we are planning to have these clusters and formation, and then once we have a full cluster that connect the whole system, then they will not longer be confined. And then we will have analogous to a phase transition. This will be a geometrical phase transition. And in this transition, we will have also the random sum of the color charges. As in U3, we will have the total charge will decrease with the particle multiplicity, and also it will increase on the average tension of the strings and also on the transfer momentum. So we have two scenarios where all the strings are fully overlapped and where they can partially overlap. So in this model, we know that the multiplicity of the particles produced are mainly due to this saturation scale that is given by the this function that is the color reduction function and is actually given by the geometric scaling function from the system for the percolating system. So there is a factorization for the number of strings that are given as a function of the energy of the colliding system for the case of the proton-proton collisions. And the main parameter is that this string density, which is telling us a geometrical scaling from the number of strings that are given in an overlap area. So in this model, there's a critical parameter which is called the string density, and it can go from 1.1 to 1.5, depending on the profile function of the partons. So the area covered when we have this full overlap formation of the connected system will be around 1 minus e to eta, where this is the density of this string. And when we have a large n limit, then we can have the multiplicity and the momentum sums that can go in this large limit as a thermodynamic limit, which goes like this. But well, this is a framework that works similar to CGC, and where we have this saturation scale that it is actually dominated by this function, which is f eta, which is the color reduction function that, as I told you, this gives us the geometric scaling function from the system. And it, well, it implicates the long range rapidity correlations in a rich structure. So we have that these clustering strings are analogous to the gluon saturation. So what we, as I told you, this was applied for the case of n large limit. So this is thermodynamic limit. But we now want to study in PP collisions, which is a smaller system, and we expect to be dominated by fluctuation effects from the initial state. So we perform a Monte Carlo where we use 3 kind of Gaussian distribution functions for our simulations. In this case, each profile function, we use 3 going from the uniform to a kind of good Saxon distribution. And we evaluate this as a function of the number of these strings, of the density of these strings. So what we found is that once we go to the critical density of these strings is reaching earlier as we go to a smaller number of these strings. And it also depends on the eccentricity of the overlap area. So this study that we found by solving this probability function of the percolation in terms of the string density, we can find this probability function, and then we can define what is the scaling function from what is the critical value for each of the systems. And here we have done for different sizes of the systems, going from 13 to 500, which is close to the thermodynamic limit. And in the case of, and we also have here playing with well, including the case of the profile functions distributions, and we see that it changes with the eccentricity for different values of the number of the different profiles, and it changes more when we go to smaller values of eccentricity, and it goes quite below the thermodynamic limit, which is this one, for the case of a smaller number of participants or strings that we have. So this means that we are far from the thermodynamic limit, and so we can find the scaling function that corresponds to this system. and as a function of the number of strings of the system. And we see that in the case that we have a largest deviation from the thermodynamic limit is the one we have less number of these strings. So just remember that this is the geometric scaling function which defines the percolating system from R for this special system, and it's proportional to the color saturation or color reduction factor. And we have also include, so since we have here we have the effect for the different number of strings. This means from the density of these strings. And we also want to study the geometry fluctuations due to different geometries in the initial state. So we first perform the elliptic case, and we start with the eccentricity 0, and then we go to eccentricity close to 1. And we see that the deviations goes farther from the thermodynamic limit as we increase in the string density. And we also have done this for the following modes of the geometry, which is triangular mode, quadrangular, and pentagonal mode. And we see the same result. And we also calculate how this critical value was modified. And we see that, again, as we go to lower number of strings, we will have this effect more relevant in the critical value. So we obtain what will be the most big modification from the thermodynamic limit for the cases of the fluctuation of the geometry, initial geometry. And we see that in the case of the triangular mode, we have the largest deviation from the thermodynamic limit. So with this, we have included now the effect of the size and the effect of the geometry fluctuations. And we also would like to include the effect of the presence of inhomogeneities, which are frequently not distributed in the total, but they tend to correlate over large distance. So for this, we use a power law that goes with the distance, and they will emit the case of the correlation decay. So we will have that the correlation exponent will be smaller than the spatial dimension that we have in the system. So this means that we will have a long range or infinity correlation in this case when we have the spatial dimension. So this is an example of how is modified the probability of in this case when we include the inhomogeneities. And this also describes how it is modified the percolation threshold when we include these inhomogeneities for the wider range. So what we do is to include how will be modified this color reduction factor by the homogeneities. And this is we see that for A, with the smaller values, we will have the larger effect on the modification for the homogeneities. And then, so we include on top of the color reduction function, deviation from the thermodynamic limit, this effect, and with some of it. So we now, what we obtain is that our new color reduction function or the geometric scaling function from this system is given by this exponent, by this expression, which is only an expression that depends on the string density. And we have this parameter. So we apply this to the data from the LHC. So we have 13 TeV to 0.9 TeV. And we see what is the corresponding geometric scaling function for these systems. And we see that they have a universal trend. And so now that we know how it is modified from the thermodynamic limit, this geometric scaling function, we would like to apply these two thermodynamic variables. So one of the interesting variables is what is what will be the effect of these initial fluctuations on the temperature fluctuation map. So we know in this model that there is a thermodynamic, we can describe the thermodynamic concept like temperature, entropy, or viscosity as a function only of this string density and the color reduction function that describes our system. So it is also related to the Schwinger mechanism for non-massive particles, and it is a way that it produces the pair of particles. So since we have that the value of the chromoelectric field is not constant and the fluctuations give a Gaussian distribution to the string tension, they can be seen as a thermal distribution on this way. And we can relate a temperature to this, to the production of these particles. So via the power law of transfer momentum distribution, we have fit for the different energies and proton-proton for minimum bias. And we have obtained our parameters for the different energies.
Grace, you have 5 minutes left.
Okay, thank you.
5 minutes.
And from there, what we obtain is by fitting that, we obtain the values of the temperature corresponding and also for the transfer momentum. So we see they both have a universal trend, and we can apply now this to the event by event fluctuations, and then from that we can obtain the correlation factor, where we will have the component from a single string, and then it will go from the sum of all the strings for a given event. So this is the result that we get for the fluctuations for the mean PT event by event. And this is what was obtained from the case of gold-gold collisions at 200 GeV. So there's also what we are more interested in is the temperature fluctuations. In this case, we have measured what it will be the temperature fluctuation by cutting on the MPT regimes and then obtaining these global temperature fluctuations for these different energies in PP. And so what we see is that they are not, they do not stabilize. So this means that when we go to the energy density plot, we see a phase transition, but since we see that the temperature the global temperature fluctuations are not stabilized, we are in a non-thermalized system. So there's also a simulation of the corresponding distribution from the multiplicities. For example, here we have done for 13 TeV, and we see that as we go to lower multiplicity, the distribution becomes less wider. So this means that here we will have a distribution for the case of larger multiplicities. So in the case of we also have see how this affects the number of sources in the model. And we see that in the case of the modification, we lower down the number of strings of the initial state. And in the case of PITIA, we lower down the number of multi-pattern interactions by a small factor. So these effects that have been found by our Monte Carlo toy model, we have seen that the calculated contribution percentage of the initial state fluctuations that is due to this initial geometry and system size, and also for the homogeneities. This is depending on the multiplicity and energy of the event. So if we take into account this effect on data, this gives us a lower initial number of the sources. And this means that when we have a wider distribution in the fluctuation, is observed to increase in high multiplicity events. So this effect means that the fluctuations will be more important as we go to lower number of to lower multiplicities, and this can be associated with the enhanced probability of the pair creations. So this can be analogous to what is the modification of the Schwinger mechanism that is also due in the expansion color flux tubes and in instability that has been done in the Glassman picture. Okay, so so this is it.
Yes.
Thank you.
Thank you very much, Irais. Very interesting presentation. I don't know if we have a question. Questions? No from the chat. The mattermost? No. Okay. If not, we thank again Irais. Thank you very much, Irais, for your contribution to this conference. And then we will go for the next talk. Okay. Which is Lydia. Hello, Lydia. Can you hear us?
Yeah, sorry, I'll just share my slide.
Good. Yes.
Okay.
Yes.
Yeah, so yeah, thank you for the opportunity to give this talk today. So I'm going to tell you about tau G-2.
Good.
Okay, so a lot of the content of this talk is based on a paper by Jessie Liu and I, and you can find more details by following the link on the slide here. Okay, so I wanted to start off with what is G-2. So roughly speaking, it tells us about how particles interact with light. So if particles are charged and they have spin, then they have an intrinsic magnetic moment. And for spin half particles, this is given by the expression on the slide. So the magnetic moment is proportional to the spin angular momentum, and the proportionality factor depends on the charge of the particle, its mass, and the so-called G factor. And so by looking at how the magnetic moment interacts with a magnetic field, Dirac was able to compute that this G factor is equal to 2. So we can imagine this by the diagram shown on the slide, where the photon is representing our magnetic field, interacting with a pair of spin half particles, so in this case, leptons. But this isn't the end of the story. So there are additional loop corrections which modify this value of G from 2. And so this is why it's interesting to look at the quantity G-2, as this is sensitive to these loop contributions. So normally people are interested in the anomalous magnetic moment A. So A is G-2 divided by 2. Okay, so why is this an interesting quantity to look at? So it's a powerful probe of new physics because there could be new particles in the loop. So one example is supersymmetry. So here you can see the photon and the 2 leptons, and then running inside this loop are a pair of scalar leptons and a dark matter particle. Other reasons it's interesting, so it's a probe of new physics, and it's sensitive to compositeness. So historic examples of this are the proton and the neutron. So the neutron, the magnetic moment should be 0 because it's a neutral particle. However, it was found to be large and negative, and the reason for this is because it's composite, so it's comprised of charged particles. Why else is it interesting? So it's a fundamental test of QED. So it's been measured extremely precisely for the electron and the muon. And in each case, there's a sort of For the electron, a smaller tension between the theory and the experiment. And then for the muon, the sort of infamous larger tension. And so a natural question to ask is, what about the tau? So we have our 3 generations of leptons with increasing mass. And so we can see that the mass of the tau is larger than the mass of the muon by an order of magnitude. Perhaps this could be explained if it was in fact composite. There's also many different new physics models where contributions can scale with the mass of the lepton. So one example is in supersymmetry, where you get this scaling and enhancement by a factor of 280. But also the models for proposed that could alter the muon and the electron G-2 could also affect the tau. So there's no shortage of theoretical models for types of new physics that could modify the tau magnetic moment. But there is a problem in that the lifetime of the tau is significantly shorter than the lifetime of the muon. So unfortunately, this prevents us from using the same techniques as we would use for the muon because the tau just decays. So we need to do something else. And so a solution to this is to use photon collisions. So we saw earlier that the magnetic moment is really just a modification, or it is really just this coupling between the photons and, in this case, the taus.
Hello, Lydia.
Yeah.
Can you please put your presentation in full screen?
Oh, sorry. Yeah. Let me see. Yeah, sorry about that.
Thank you.
Okay. Yeah, so a solution for this is to use photon collisions. Okay, so where can we get a source of photon collisions from? So if you have a charged particle, then this is surrounded by an electromagnetic field. And so if you have 2 charged particles and they pass close to one another, then their electromagnetic fields can interact and produce new particles. And so this is exactly what was done in order to get the current constraint on the tau magnetic moment, which is in the PDG. So back in 2004 at Delphi, this was done. So they studied photoproduction of a pair of taus. And the cross-section for this process is sensitive to the value of the tau magnetic moment. So you could imagine sort of loop contributions being included at these vertices and modifying the cross-section. Okay, so now we can again ask the question, that there's these tensions seen for the electron and the muon, what about the tau? So here we show the anomalous magnetic moment, and so the top line is for the electron, where the error bar is scaled up by a factor of 10 to the 9. Next, we have the magnetic moment for the muon, where the error bar is scaled up by 10 to the 6. And finally, we have the constraint for the tau, where the error bar is not scaled at all. It's just really very large. And then finally, we have our standard model prediction with a much smaller error bar. So here it's really the uncertainty on the experiment, which is limiting our ability to really test the standard model. And so we're not even sensitive to the sort of one loop QED contribution calculated by Schwinger given here. And so really this is an area where we can aim to improve the measurement. So can we beat it? There's many interesting proposals for the future using Bell 2 or using upgraded colliders or using so-called bent crystals. So there's a lot of interesting proposals. But the question we asked ourselves is, what can we do right now? So using data that we already have. And so we then come to realize that the LHC is also a photon collider. So the LHC is also colliding charged particles, protons and lead ions. And so with protons, there's a higher center of mass energy, and with lead ions has a lower center of mass energy in smaller data sets, but there is an enhancement in the photon flux because of the high charge of the lead ions. So in our study, we focus on lead-lead collisions for reasons which will become clear. So just first to show a contrast. So this is the sort of usual head-on collision, lead-lead collisions that we're familiar with. And so this is an event display from the ATLAS experiment. And I just wanted to contrast with this with ultraperipheral collisions, where our ions pass by each other and their electromagnetic fields interact, and they're extremely clean events. So here you can actually see a di-tau candidate. So there's an electron and a muon here. And so basically the data is already recorded by the experiments. Okay, so ultraperipheral collisions are super clean with negligible pileup. They take about a month to gather at the LHC, or we gather data with them for a month a year. There's very low trigger thresholds, so we can trigger on these very soft di-tau events. And so we've quantified the potential of using these collisions using Monte Carlo. So we used MADGRAPH with a modified photon flux, Pythia, and then a Delphi simulation of the ATLAS detector. Okay, so this is the process. So photo production of a di-tau pair, but now with heavy ion collisions rather than electrons as used at LAP. And so this process hasn't yet been observed at the LHC. Okay, so how can we look for these types of events? So this is just a brief reminder of tau decays. So the tau is the only lepton which is heavy enough that it can decay into hadrons. And so the largest branching fraction is the so-called one-prong decay, where the tau decays to a charged pion, a neutrino, and other neutral pions. Next is the leptonic decays, which is shown here. So it decays to a lepton and 2 neutrinos. And finally, we have three-prong, where it decays to 3 charged pions, a neutrino, and neutral pions. Okay, so for the backgrounds, we generated photo production of dilepton pairs and diquark pairs. And then we selected signal regions to target di-tau production. So we use the lowest available object thresholds, which are used within ATLAS. And so for our signal regions, we require at least 1 tau or we select events where at least 1 tau decays leptonically in order to reject hadronic backgrounds. And then for the other tau, we reconstruct it as a single track to target the 1 lepton and then 1 prong decays. So the tracks have a much lower momentum threshold. We then have 1 lepton plus 3 tracks targeting decays where 1 tau decays leptonically and the other decays to the 3-prong signature. And then 1 lepton plus 2 track where for the 3-prong signature, one of the tracks might not have been reconstructed. And so for the 1 lepton 1 track case, you have a large background from dilepton, so photo production of a pair of electrons or muons. And so we reject this by requiring that the lepton and the track are not very back to back. And you can see that this rejects a lot of this background. Okay, so then we move on to setting constraints. So we use standard model effective field theory to modify the magnetic moment away from the standard model. And so here you can see the distribution for the signal for the standard model in black, and for modified magnetic moments in the colors. Some of them are also modified electric dipole moments, which I won't talk about today. So we can see that when you change the magnetic moment, it can alter the shape of the lepton momentum distribution. So as well as the cross section, this gives us an additional handle on how to distinguish standard model from beyond standard model. And so putting all of these components together, we assume that we observe the standard model and we quantify the constraint that we could achieve using a chi-square. So here we can see chi-square versus the deviation from the standard model. And so as you go further away from the standard model, this chi-square gets larger, and so it's more and more incompatible with the predicted yields from the standard model. And so here we've summed the chi-square for our various signal regions and assumed a 10% systematic. And then if we exploit these shape differences by splitting our bin in lepton momentum, then it further improves our constraints. And so now we can again look at the constraints on the magnetic moments. So the top half is familiar. So these are the existing measurements for the electron, the muon, and the tau. And then in green are our projected constraints using LHC heavy ion collisions. And so the top is using the current data set and a 10% systematic. And then we look at scenarios where you half the systematic and you increase the data set size. And so the message from this is that using these collisions, we should be able to surpass the current constraints from Delphi, or even better, when we look in data, hopefully discover a tension with the standard model. And so just to summarize, tau g minus 2 is an interesting and important quantity, but it is barely constrained. However, LHC photon collisions offer a promising solution to improve this measurement and also for many other interesting scenarios. So I'll just leave you here with a summary of other ICHEP photon collision talks on various topics. Thanks.
Thank you very much, Lydia. Now it's time for questions. I don't see a question from the chat. Let me see if we have something from the Mattermost. No. We have still some time to discuss. So here you are commenting about the contribution from Alice. Can you say something about this, about the Alice experiment?
So here we've used a simulation of the Atlas detector. So I don't believe anyone has really studied the potential for Alice.
That's why I'm asking.
Yeah, so I think it's definitely an interesting question because they have superior particle identification, so that's interesting, but I believe they have lower luminosities.
Yeah.
But yeah, I think it would be something interesting to explore.
Sure. That's quite interesting thing to do in Alice and on some other experiments.
Yeah.
Okay. Thank you very much, Lydia. Very nice contribution. And now we are giving the floor to Vitaly.
Can you hear me?
Yes.
Okay, great. So I will share.
Please share your screen.
Okay. So it's full screen, yes?
Yeah.
Okay, great.
So
Okay.
now we have a contribution from Vitaly Osvenchenko.
Thank you very much. So good afternoon. First of all, I would like to thank organizers for giving the opportunity to present our work here. In particular, I will talk about the fire streaks, electromagnetic effects, directed flow, and lifetime of the plasma at SPS energies. This work was done in collaboration with members of our group are listed here. And actually, our work was published in the series of PRC paper, and the electromagnetic part actually was just recently published in PRC. So here's the outline of my talk. I will start with a brief introduction and motivation. Then I will describe the model which we are using. And then I will come to electromagnetic effects in peripheral lead collision. In particular, I will talk about the initial conditions which we are using and in fact about the results. And finally, I will summarize and give some outlook. So we study the electromagnetic effects in heavy ion collisions, in particular in peripheral lead-lead collisions at top SPS energy. After the collision, the positively charged spectator generate electromagnetic fields which modify the trajectories of charged pions. We use this effect as a new source of the information on the space-time evolution of the system. The NA49 experimental data on Feynman X dependence of pi plus over pi minus ratio, which is shown here on the left plot, shows a strong electromagnetic effect, especially for pions with small transverse momentum, which is shown here by blue line, and especially in the vicinity of the spectator. These results can be reasonably well reproduced by Monte Carlo model by introducing so-called emission time dE. This emission time, or you also can call it emission distance. This distance defines the initial distance between the pion emission region, which is reducing this Monte Carlo model to a single point in space, and the spectator. We adjust this model to 3 basic experimental data sets on charge dependence of particle production, and more details can be found in this paper. And we obtain that faster pions are produced closer to the spectator system, as shown on this bottom plot. So it motivated us actually to construct the model where all those findings will be included. The idea of the model was proposed by Anthony Shurek. And this model describes the longitudinal evolution of the system and what we are doing. So we divide the colliding nuclei in transverse plane in 2-dimensional 1 Fermi over 1 Fermi bricks. After the collision, the object of matter, which we call fire streak, is formed. The fire streak are moving along the collision axis. And each fire streak fragments independently in pions by single fire streak fragmentation function parameterized in the following form, where ES and YS stand for the total fire streak energy and rapidity of fire streak, and they are both given by the energy momentum conservation, and the total mass of fire streak, MS, is equal to the sum of brick masses, and it's given by the collisional geometry. And finally, A, sigma, Y, and N are the only 3 parameters in our model. And they are fitted to the NA49 experimental data for the rapidity distribution of negative pions. And it appeared that they are common to all fire streaks and independent of lead-lead collision centrality. So one can claim that our model by construction is able to describe the whole centrality dependence of the rapidity distribution of negative pions, including in particular the narrowing of the rapidity distribution from peripheral to central lead-lead collision, as illustrated on this plot. So now actually I'm coming to the study of the electromagnetic effects within the framework of our model. We start with the initial condition. We start with the description of initial conditions of the system which we are using. We use the initial rapidity distribution of negative pions obtained from our model that I just presented. And actually this is a feed to the experimental data shown here on the left plot. And our model describes only the longitudinal expansion of the system. Thus, for the initial transverse momentum distribution of pions, we choose one obtained from UQMD model, which, as you can see on the right plot, reasonably well describes experimental data for the transverse mass spectrum of negative pions produced in peripheral lead-lead collision at top SPS energy at mid-rapidity. The resulting UQMD prediction for transverse momentum distribution of pions at mid-rapidity we parameterized by the exponential function presented here, where S, capital S and T stand for yield integral and the inverse slope parameter respectively. The fit gives us two values of inverse slope parameter separately for pi minus and for pi plus. You can see both fit. On the left plot, there is a fit for pi minus. On the right plot, there is a fit for pi plus. And it gives T equal 165 MeV for pi minus and 163 MeV for pi plus. In general, the inverse slope parameter may depend on rapidity. However, we perform the study on rapidity dependence of the inverse slope parameter and figure out that the results of calculation of electromagnetic effects do not depend much when changing the inverse slope parameter with the pion rapidity. That's why we assume that the inverse slope parameter does not depend on rapidity and equal to its mid-rapidity values. To start the calculation of electromagnetic effects, we have also to fix the time of emission of pions from the phi streaks and initial position of the pion relative to the spectator system. This cannot be calculated from the first principle and is treated as a free parameter in our model. We introduce the pion emission time in the phi streak rest frame. Up to this time, the phi streaks evolves in longitudinal direction. The actual position of pion creation in Z for each phi streak in nucleus center of mass system can be obtained by Lorentz transformation. And it's important to mention here that the transformation depends on the velocity of a given phi streak in center of mass system, which in our model depends on its position in the impact parameter space. So now I'm coming to the result. And first, we start with a comparison to the previous study, which was performed by Andrzej Rybicki and Antoni Szurek like approximately 10 years ago. And in the previous study, the emission region or the pion emission region was reduced to a single point in space, and it was XYZ is equal 0, 0, 0. And the initial pion two-dimensional XFPT distribution was taken from nuclear-nuclear collisions. This result is shown on this plot by red line. Now we are trying to study the effect of a phi streak model on this electromagnetic effect. So we step by step include new developments. First of all, instead of a single point in space, we extend our emission zone in transverse place by taking actual position of phi streak obtained by collision geometry. And another thing, as we just discussed, that we are taking now real rapidity distribution from our model and the transverse momentum distribution from the UQMD model. In both cases, the pion emission source was static in position space, and the pion emission time was set to d equal 0.5 for me in collisional center of mass system. And so this results for the new current study is shown here by blue line. But it's important to mention again that the pion emission source was static for both cases. But now we finally introduce the longitudinal evolution of the system along the z-axis given by the phi streak velocity. Consequently, we introduce a pine creation time tau for each file string. And we perform simulation for various values of tau for 0.5, 1, 1.5, and 2 for meter. And all of them are shown on this plot by different colors. It's important to say here that the values are in the rest frames of individual file strings. So please note that the values of pine creation time in nucleus center of mass system are different due to the different velocity of file strings. And one can conclude from this plot that there is no configuration which describes the experimental data on whole range of ICHEP with a fixed tau. So if you take a fixed tau, then you cannot describe the ICHEP dependence of pi plus over pi minus ratio in the whole range of ICHEP. That's why we decide to try some functional dependence, some tau which is not fixed. As a first try, we use that our tau emission time is proportional to the excitation energy of the file string, and with the formula, so it's the formula shown here, and we set that the minimum tau is equal to 0.5 for me, and the maximum is we set to 2 for me, which give us a coefficient of proportionality, which is equal 0.08. And on this plot, I show the results of the calculation of electromagnetic effects for the pi plus or pi minus ratio as a function of ICHEP for two different transverse momentum beams. And the red line corresponds to the results obtained from our model with tau, which has dependence written in this way. And all the results presented here were shown for stable spectator, but it was shown in particular by Kasia Mazurek and Antoni Szczurek that the spectator at this energy is actually it's not stable system at all, so it's very excited. And that's why we introduce the expansion of spectator by introducing the radial expansion velocity for the spectator. And we found out that the configuration with the expanding spectator with a velocity equal 0.2 gives the best description of the experimental data, and it's shown here by blue lines. Another things which we want to study the influence of particle flow in our calculations. So the particle flow is quantified in terms of Fourier composition in the following way, where coefficients V1 and V2 is actual directed and elliptic is called directed and elliptic flow respectively. And there is available experimental data for these coefficients as a function of rapidity and PT obtained from an A49 and WA98 collaborations. And we fit those experimental data and introduce them into our model and try to study the effect of flow into electromagnetic effects. So, and we found that for V2, when you introduce V2, there is no change of pi plus or pi minus ratio as a function of ICHEP, but there is not small but not negligible effect for V1. It's shown here by green line in comparison to the blue. So blue it was without flow, and green is with flow, and you see there is a tiny difference for ICHEP larger than 0.2. But for to say it again, but for V2 we have no difference at all. And another effect to be considered is a well-known phenomenon of vorticity of strongly interacting matter. This effect is potentially important as the rotation of fire streaks driven by shear viscosity will modify the trajectories and consequently also the position of pine emission with respect to the spectator system. We estimate this effect in the following way. We rotate each fire streak for a given small angle, alpha. After the rotation, the fire streak follows its modified trajectory until pines are emitted from the fire streak. And the pine emission point is shifted in transfer and longitudinal direction with respect to the case with no rotation. And the size of this shift increases with increasing the angle alpha and the pine emission tau. And we can estimate the size of this angle using the available experimental data on V1 as a function of rapidity from an A49 and WA98 collaborations. And we found that the best description of the experimental data gives the rotation by alpha, which is equal 1.75 degrees. So it's very small angle. And another important thing that this data, the directed flow V1 is very sensitive to this angle. For example, I show on this plot by blue line the results for when we perform rotation by 3 degrees, and you can see that the directed flow is highly overestimated compared to the data. Even if we increase the alpha only by a bit more than 1 degree. So it's very, very sensitive. And so then we introduce this rotation into our model and we try to study this effect on the particle ratio. And we found no significant change with respect to the case with no rotation. And this can be explained because of small angle allowed by the experimental data. So it means small displacement of the pine emission points compared to the case with no rotation.
Hello, Vitaly.
Yes.
You have 3 minutes left.
Yeah, actually, I'm coming to my summary. So we introduced the model of the longitudinal evolution of the system, which explains the centrality dependence of pine yields. And also we implement the initial conditions for pine production provided by our model to study the electromagnetic effects in peripheral lead collisions. And so we found that rather small pine creation times have been necessary to describe the data on electromagnetic effects, which concern faster pines. So tau is in the range from 0.5 to 2 Fermi. Configuration with the expanding spectators gives the best description of the data. And inclusion of directed flow gives a non-negligible effect, whereas elliptic flow shows no effect. Rotation of fire streak results in the presence of directed flow. And finally, small angle, smaller than 2 degrees, is needed to describe the data. And the last things, I want to present our outlook. So what we are doing actually right now and what we are planning to do in the near future. There is two very nice sets of experimental data obtained from STAR and recently from Ali's collaboration on V1 as a function of rapidity for pi plus and pi minus for STAR, and this is for positively hadrons and negatively hadrons for Ali's. And in case of STAR, you can see that there is a charge splitting. And we believe that this splitting causes by electromagnetic effects. And actually, what we did, we calculate such a quantity, which is actually the difference between V1 of positive and negative pines. And so we constructed this quantity having the experimental data, and also we performed the calculation using our model with a fixed parameter tau, which is equal 4 Fermi, and we obtained very nice description of it. So we believe that the splitting of V1 for pi plus and pi minus is due to the electromagnetic effects, and we actually can reasonably well describe it within our model for star energies. And so we want to try it also and to see what it gives us for the LHC energy and to compare it to the results presented recently by Ali's collaboration. Thank you.
Very good, Vitaly. We have a question from Yuri.
Hi, Yuri.
Yuri.
Yeah, hi. So I basically have several questions, but essentially I can group them in the following way. So you're saying that basically this fire streak thing describes the longitudinal dynamics,
yes,
and on top of that you take transverse dynamics from your QMD.
You're right.
Probably breaks the overall energy balance, but then I'm basically wondering, I mean, wouldn't it be better and more consistent to simply take your QMD for everything? That's just more consistent, and then study the electromagnetic effects on top of the pions emitted from your QMD, which seems to be a reasonable way to do. And the other thing is that you basically only have pions, but actually at lower energies, you have significant number of protons and other particles. So basically pions actually become minority at lower energies.
Yeah. So concerning the protons, that's what we wanted to also to see, and especially we want to check if you are familiar with the NA49 data. There is a energy change of energy of sign for V1 of protons for the specific energy, if you remember it. So we want to check, does our model gives us the same as change of sign for V1 of protons if you go down with energy. But concerning the UQMD, that we are interested in very in a regime with a very high rapidity. Yes. So we are doing ICHEP, which is larger than ICHEP of spectators. So rapidity is above 3 in our case, and I don't believe that UQMD works for this rapidity at all. So that's why we are not using it. Yeah.
Okay. Any comment, Yuri?
Yura?
Well, I really don't understand this because most of the plots which you are showing are basically for mid rapidity.
No.
So,
okay, I will show you again.
The V2 transverse momentum spectrum, that's all.
So the
and
most interesting part is above 0.2 ICHEP, yeah? But ICHEP 0.2 is above, so you see the vicinity of spectator in this plot for this energy is 0.15 ICHEP. So everything which is above 0.15, it means above, the rapidity is above of the beam rapidity. Around 3.
Yeah, but I mean basically the rest of the plots which you're showing, not the plots as a function of XF, but basically V1, V2, PT spectra, everything else, it's basically for mid rapidity where you simply take your QMD results. So that's why I'm wondering why don't you just use your QMD?
We have a question from Shurek. Probably he can.
No, it is not a question. It is rather a comment to the question of Yuri. So as Vitaly has shown, we are going to rapidity as big as 3. So this is almost beam rapidity for this highest SPS energy. So it's really large rapidity. And the use of ORQMD is completely technical. We need some tool which gives us a reasonable description of the data without electromagnetic effects. And on the top of this, one has to include electromagnetic effects. So we thought that this fire streak model is a development. Maybe not everybody realizes this, but we think it's much more physical than other initial conditions for heavy ions. We think it's very important condition, initial condition for heavy ions. Therefore, we wanted to use something which we believe is the most appropriate, especially in this context of space-time development. I think many models on the market do not have correct space-time development of the plasma or at these SPS energies. Okay, that was my comment.
Yeah, and having the possibility to use not UQMD but our model, for example, it gives you can study the time evolution of pions. Well, you can study this tau when it's created, but because UQMD doesn't give you such an opportunity, it gives you just a spectrum, that's it, yes. But having this model, we can really study the effect. We can study when the pions are created, the effect of QGP, let's say, yeah, how long QGP exists, and so on and so forth.
Okay, but then I'm confused by your slides 5, 6, 7, 8, and 9, where you basically show that fire streaks extend between the spectators, not outside of spectators, but between the spectators. So yes, exactly this sketch on the left. So, your fire streaks extend between the spectators, and they are basically proxy to describe the dynamics at small rapidities, actually. That's what you show here. That's what you show in those plots.
It shows feed because it shows only the available feed, available data, yeah? The experimentalists have only this. So we use this feed, but we are working actually on this regime, yes?
Okay, so the sketch on the left is basically misleading. It does not describe what you're actually constructing.
Sorry, but please look to these vectors, green vectors. These are velocities. So some part of these fire streaks move in the direction of the spectator. So the one which is the closest to the spectator goes almost with velocity of the spectator. This is the idea of this dynamics at low energy.
So the idea of this model is that the faster pions are created closer to the spectator. So it means that those pions on this scratch, which goes close to the spectator, goes fast in Z direction.
Okay.
Thank you, anyways.
Yes, it's very nice, very interesting discussion. But I think it's time to close this part of the second heavy ion session. Thank you very much.
Thank you.
To speakers of this part of the session, and we will resume as it is indicated in the program at 6:06. So now it's time for coffee break. Thank you very much to everybody.
Arturo?
Hello?
Yeah, so I see that speakers from the second part that are connected now, so maybe we can go and test.
Yes, probably we could use this time to check the video, the sound from the next contributors. I think Daniel is there. Hello,
Yes.
Daniel.
Let me. Yeah, you say you cannot start. Just got a message. You cannot start a screen share with the others participants sharing. So someone is sharing.
Now it's fine. There were organizers.
Now it's fine.
Yeah.
Okay. Yeah. Okay. Let me see that.
You can also check your camera if you like.
Okay. Let me see.
Good.
Do you see my screens?
Yeah.
Okay, let me do full. Okay.
Full screen.
Is it good?
Yep.
Okay, very good. I probably prefer not to use the camera because I don't think my connection is so good here in my house. So for the
No problem.
okay,
Very good. Thank you, Daniel.
I'll stop.
We're all set.
Thank you.
Okay, see you in a few minutes.
You want to test the other people? Or?
Yes, yes, please. Can we try Alexander? Alexander Blinkin? Alexander, are you around? Agnieszka? Tusak? No. Yaroslav?
Hi, could you hear me?
Yes.
Hi.
Is it Yaroslav?
Yes, yes, yes.
Good.
Yeah, that's me.
Can
Okay.
you try sharing your screen, please?
Okay, you should see now my title page.
Very good. Very good. Okay, thank you.
Okay.
We're all set. And
Okay,
what
I will
about
release the screen.
Valerie?
Oh, where is?
Stop sharing, please.
Yes, done.
Good. Now, Valerie, are you around? That's fine. I think they are having the coffee because this is coffee time now.
Okay, we should also get some.
Okay, yes, we will also try one. Thank you. See you in a few minutes.
So do you hear me?
Yes, I can
Yes,
hear you.
yes, we can hear
And
you.
see the slides, right? Okay, great.
Can you please try sharing your screen?
Yeah, I'm sharing now. So I forgot to press share. Yeah, do you see now? Right?
Thank you.
Okay,
You are
thank you.
outside. See you in a few minutes. I didn't see your full screen working.
Sorry?
Can you try again, please?
I did. I saw his full screen.
You did it. Okay. Okay. So, see you then in a few minutes.
Hello, good afternoon.
Hello.
Can you hear me?
Yes.
My name is Agnieszka Luszczak. Can I check my slides if I can share or later?
No, do it now. Just
Okay, thank
that
you.
everything works, please.
Share screen.
Co robiłaś?
So you are Agnieszka
Nic nie robiłam, no share screen.
Tuszewski.
Tuszak. Please try to share your screen now.
Yes. There?
Okay. Good. Very good.
So it
Works perfectly. Now it's
Thank you.
fine. Okay. Thank you very much. See you in a few minutes.
See you.
Stop sharing your screen now.
Unmute.
In the bottom part, yes. Good. Thanks.
can I start broadcasting my slides just to make sure the full screen works? Thank you.
Yes, yes, you can. You can do it, please.
Okay, let me see.
Espera.
Does it work? Do you see?
It works.
You see
Hello,
my...
Daniel.
Can I start broadcasting my slides just to make sure the full screen works?
Daniel is sharing your the screen.
Yes,
Yes, you can. You can do it, please.
Okay, let me see.
Yeah. Hello, Daniel. Are you there?
Yeah, I'm here.
Good. So we have still 1 minute to start. If you want, you can start sharing your screen. Yes.
Thank you.
And it's almost time to start. I think now we can start the second part of this heavy ion session, the second heavy ion session from this conference. And we have the pleasure to see the presentation from Daniel Tapia-Takaki, who is going to talk about quantum tomography for collider physics. So please, Daniel.
Well, thank you very much for the opportunity to present this work in collaboration with John Martens and John Ralston from the University of Kansas. And as you mentioned, we will talk about quantum tomography for collider physics that can be applied for heavy ions, but also for proton-proton. And just in a nutshell, so what this work is that we bypass many years of theoretic formalism and particle physics structure to describe physical systems, and the way we do that is in a model independent way, using just basic quantum mechanics, as I will describe today. One thing we know from school books is that they talk about wave functions, many of them, and not much about density matrices. So this talk will be mainly about density matrices, and in particular how from the experiments could be inclusive or measurements or even exclusive measurements, how we can measure this density matrix, and in these ways trace down the larger one, the one for the system that we want to describe. And one thing is that quantum mechanics currently is living a renaissance thanks to what's happening in quantum optics, quantum lasers, and information science and so on. And indeed, the theory has evolved, and Copenhagen, when passes pool date. And one of the things that we have to do now is to sort of delete these internet cookies that we learned from that, and start also looking at the data in these new ways. And this is this talk addresses this point. So one of the things you see in this handbag diagram is the typical sort of deep inelastic scattering process. And you want to describe the system that could be like proton structure, nuclear structure, or something underlying like what's happening in heavy ion collisions. And the things that you measure or you study is for example, the muons or the leptons or something like that. That could be you probe the things that you probe in the system, and you want to determine the density matrix for the ROEX. And one thing is that if you make it in quantum mechanics, you don't have to make assumptions about perturbative theory or one photon exchange. So this is something that we normally measure. We measure the experimentally like angular distribution, dn, d cos theta, d phi. And in quantum mechanics, this observable, this measurement is proportional to the trace of two density matrices: the density matrix of the probe, the thing that is known, and the things that you want to characterize the unknown of the system. And that's just a basic formula that you have from basic quantum mechanics. And I will begin, because we have little bit of time, I will start talking first about some data. This method can be applied to many studies. So we applied here some data from ATLAS. This is a topic that has been very popular, Drellian production in proton-proton physics and also in heavy ion. And the reason for that is because we know that the next to next linear order, QCD, is not working very well, and there are this expectation for the Lamtung violation. And one way that this can be done is to measure the angular correlation of this Drellian. And this is done through this angular expansion. So ATLAS and also CMS in this conference, they are showing these A0 and A-1s, which are one of the old-fashioned way how this is computed as a function of PT of the Drellian. And what you see indeed is that the data, there is this discrepancy, tells you QCD is not working very well, and people were very interested. Now, the ATLAS study has all these numbers, very big details, and we have used their data to apply quantum tomography, and so give you study it and show you also some example. So what we have done is that we can compute the eigenvalues and the expectation values through quantum mechanical expectation values from the ATLAS data. And we did that as a function of PT of the Drellian. And one thing already you see here is something quite interesting. You see a crossing of this expectation or eigenvalues here, which is very interesting, and we have not seen any precedent for this. And why we think it's interesting is because traditionally, when people are looking at something like resonance production, you look at invariant mass distribution, right? And but the problem of that is that you ignore the angular distribution. But we know that when there is something happening, there is the eigenvalues will cross, and so this is very, very interesting. And another way that we have seen this is through the entanglement entropy, because from the ATLAS data we computed the density matrix, so we can compute the S, which is given by this formula, and we do this as a function of PT, and we see indeed that the entanglement entropy increases about 60 GeV precisely at the point where the eigenvalues cross, and this tells us that there is something there to characterize. Now, let me tell you a little bit more about the method. So quantum tomography, just in a few words, is building higher dimensional structures from lower dimensional projections. And the lower dimensional projections are the measurements that you make, okay? And these projections, we call it here GL. And from there, we relate the observables that we have, that we make, these expectation values that could be this angular distribution in terms of the ROEX, that is the unknown of the system. And then from here, you can, this is done in basic quantum mechanics, you can reconstruct the density matrix of the system in terms of the things, in terms of the probe. Okay, and of course, one of the questions is this a complete reconstruction? And the answer is that it's complete for what it expands. And if you look at our study, you will see very interesting discussions about this as well. Now, one thing I mentioned at the beginning is that quantum mechanics has is evolved. So this way of doing quantum tomography, which is discussed, is tell us that the wave function indeed is observable, the density matrix is observable, and of course the wave function is just corresponds to rank 1 density matrix. But the systems that we have in general, you must start with the density matrix. Now, the procedure that we have established is very easy and can be used for analyzing data. Basically, if you have data, you can compute the density matrix, and this can be done for the things you measure, 2 particles, 2 jets, or plus anything else that you have. And the procedure is that you start with these 4 vectors, and you can compute the total pair momenta and vector difference of them, and then you can express the angular distribution. So in this publication, recent publication, we explain all the method and procedure and examples. So I invite you to look at it. But just here in the interest of time, just tell you that this d sigma d omega is the things that you get from data, and then this is related, as I said, to the trace of the product of these 2 density matrix of the probe and X, and then from here you can reconstruct the density matrix. This is precisely what the quantum tomography is, okay? Reconstructing this density matrix. Now, just to give you an example, you know, the example that we have discussed is this Drelian from the Atlas data. And of course, you want to say, what is the density matrix for the probe, for these dimuons? For this particular case of 2 massless fermions, we know this density matrix just from pure symmetry. This again is something that you do in classes in school and in college. And so one thing we know is that this density matrix just depends only on 2 parameters, A and B, that can be obtained from standard models and a lot of calculations. And all these calculations, basically the only thing they predict is for this probe is just 2 numbers. And these 2 numbers, when I say that we bypass this, is because we don't need actually to get these numbers from the predictions. We can obtain these numbers tomographically from the experiment itself. And indeed, this is something that we did. And for that reason, you know, sometimes less theory is probably better theory for analyzing these processes. And the fact that you have density matrix, you can also put very easy constraints on positivity for the data, which is also a big issue in many analyses. Okay, so in the study, we also introduced one interesting procedure for what we call the mirror trick, where we mirror all the components from the density matrix of the probe into those of the systems, and this allows to get the reconstruction of the density matrix from the system, and this is discussed in our study. So how do you start this in practice? So in practice, it's very easy. So you have first to start with a Lorentz invariant method. So we start with measurements, for example, in the lab, okay? That you measure the jets or the muons or a gamma photon. And you first write it in this way, and you don't need to then deal with all these different frames. That is always, it's been a big issue in many comparisons. So this is the first thing we do. And from there, we measure the angular distributions of the process that you want. And let me tell you a little bit more about this Atlas data analysis we did, because it's quite interesting. Once we have the density matrix and the characterization, because we have the angular distribution, we can actually displace the spin parameters of the C boson that we reconstructed. And this diagram that you see here is the sideways view of the frame, of the frame that we use for this covariant, which is this Collins Soper. And for, you know, sadly in the literature, people don't display it this way, but that's the way it looks like. And here you see this line here is the the beam axis. So you have here the X, Y, and Z plane where the C goes out of the page. And then here we can display this arrow is just the unit vector for the spin vector of the C going in this direction, and we can do that for all the data that we have analyzed, not just for here. And so here is what you obtain. So this is again the beam. This is the Z-axis, and we are doing sort of holographic view in the lab frame of the C spin components, and this is how they look like. And one of the things is that you have seen that the quantum entropy changes, right? And one interesting question could be, what is the fraction of the data from Atlas that corresponds to a polarized pure state? Right, something that can be described just with the wave function. And the answer for that is that only 2% of the C's from the data we analyze are pure states, which tell us that we need to have the whole mixed state, and this is because it's not separable. This is indeed an entangled system. And we can look at this 2% of the C to see how they look like in this X, Y, and Z plane in the lab frame. And when we look at those 2%, we see that they show this, the spin parameters, they show this vorticity. So these C's are spinning as shown in this picture. And this probably tell us something about about what's happening in the system. And we're currently exploring this a little bit more detail with the, and now let me give you another thing which is also very relevant for the discussions in heavy ion. So in heavy ion, there is a lot of measurements about back jets, gamma jets, and correlations and things like that. So just for illustration and make kind of a prediction, we have looked at 2 jets events. So we don't have detailed studies like the one from Atlas for the jet, but we can take generated events from DIS, like using RapGap, and apply this quantum tomography. And what we have looked is at the angular correlation of these 2 jets. Okay, and this angular correlation is expressed by this phi, so it's given by this plot that you see here, all these points. And then using the tomography, we can make a fit to all the possible moments that are required to describe the data. And what we see is that indeed we need up to several components to describe it, and that tells us that there are some interesting features that we're currently exploring, and definitely also tell us that we cannot separate the polarization, longitudinal and transverse components, degrees of freedom. So this system is entangled, and I believe this will have maybe some interesting consequence for future data, where very easily, just from the 4 vectors, you can compute these correlations. Now, in summary, let me tell you that quantum mechanics is experiencing definitely a renaissance. And this opens the opportunity to study QCD in new ways, in a model-independent way, like quantum tomography. We have studied this procedure in the publication we have, but we also look at the muons and the jet, and can be expanded. So with the data that is already available and the future data sizes, is feasible to do these procedures. We have already a Lorentz invariant formalism, which expedites analysis using the 4 vectors in the lab frame. Quantum tomography, let me stress, will provide you much more information than simple moments. Many studies that has been done has been just limited to moments of a distribution. And of course, this is interesting, but if you use quantum tomography, you have access to all moments and to much more richness of the system. Now, the thing is that, of course, you want to compare to theoretical calculations. So quantum tomography will give you independent eigenvalues and eigendistributions, I just showed you. And also this comes with Born rule probabilities. And so because of that, it's a natural topic to compare to theoretical calculations. So although this is a model independent, theory independent procedure, you can, with these results that you obtain from data, you can make comparisons later with theory. We have applied this procedure with Atlas data for Drell-Yan production in proton-proton, and we see interesting features that has not been revealed by the analysis that were done. And we believe that this is due to quantum entanglement because of what I show you. And we are starting applying like this for other processes like that jets that we believe will be very interesting also in heavy ion physics. Thank you.
Thank you very much, Daniel. It's quite interesting presentation and new analysis. Let's see if we have some questions from the attenders. No, from the chat. Let me see from the uttermost. No, I don't see any. Yes.
Maybe a very basic one, Federico Antinori here. Ciao, Daniel. In the Drell-Yan production, what is entangled with what? This is a very basic question for me.
Okay, so in the entanglement, so the quantum entanglement can be measured in terms of this quantity,
yes.
S, right? And so the basically tell you if you have a pure system and an impure system. So if you have a pure system like a wave function, then it means that you know it's not entangled, right? And so the fact that we see that only 2% of the data it corresponds to pure system, it means that the description of the Drell-Yan requires a mixed state description. So what is
I understand the formula, but physically,
yeah. No, I'm just explaining this for the others. I know you know this, just the basic. Now, what is the entanglement? So one thing we are studying at the moment is the following. In the Atlas data, Federico, the people are looking at this variable. So this is one of them, the Slantum relationship, and they see that this is due to this next to linear correction, right? So one thing that we don't know is that if what we see is a consequence of this additional correction that is happening here. In the Atlas and also now in CMS, they have measured like different ratios because originally for many years, they thought that there was only one Lamtung rule that was violated in QCD. But actually, we're showing on a study, and also other people have shown after, that there are two more rules that violated in QCD. And so to answer your question, what is the consequence of entanglement? So we are studying this at the moment. We don't know whether it is related to this fissure here.
Yeah, no, but okay. I think that then we can have a coffee together. But my question was even more basic. In my mind, entanglement is when you have two wave functions in a sense which are not independent, and I was wondering which wave function are those in this particular case.
Yeah. So basically, there are some features of the polarization. So basically, what happens is that they are entangled the polarization component with the traditional, space and momentum component. So these two things are entangled. Yes.
Okay.
Thanks.
I'll think about it some more.
Okay, well, Federico, but we should discuss.
Yeah.
Good. We have one last question from Zurich. Please go ahead.
Hello, Daniel. Anthony is speaking.
Hi, Anthony. Here.
Hi, nice to hear you. I only joined in the middle of your talk because of some other tasks. But this Lamtung violation, for instance, this picture which is now on display, can be understood, I think at least some people try to understand as transverse momenta, because these Lang-Tung relations were obtained for collinear approach. When you include transverse momenta, I think you are approaching this data. But if you are saying that this may be due to entanglement, so you are saying that there is something wrong with QCD, don't have correct entanglement. What you are saying?
Yeah, no, no one said that this fissure may be like this vortex, things that we say. We're investigating whether this is related to this. But as you know, I know your paper, Anthony, about this Lang-Tung. But what we know is for sure that the picture is much more complex, right? Because there is not just one rule that is violated, but we know now that there are three, right?
Okay.
You agree, right? So there is, it's
Yes.
not just one. So, and
yes.
So I know that. I mean, these next to other people, this is a big business for them. So, but okay, let's discuss.
But I want to say that those people think when going to higher orders, they will be able to describe this, because I think this Lang-Tung is violated at higher orders. So
yes,
this can be effect of higher orders, and those people are not talking at all about entanglement, not in this.
No. You are totally right. So you are totally right. So that's something that we are currently trying to. Okay, maybe let's discuss more in private, because
okay. There's no time. Thank you.
Yeah. I have some ideas, but I don't know whether my collaborators, all of them, agree.
No. Okay. Thank you, Daniel. Very much.
Thank you, Anthony. Thank you, Federico and Daniel. Thank you very much. And now we pass to the next talk. Thank you again, Daniel. You can stop sharing your screen. Thank you. And now, Alexander Wilinkin, please. Can you share your screen?
Yes. Do you see my slides?
Yes, we can also see your video. So we will hear from Alexander Wilinkin the recent results on the practice and exclusive process with heavy ion collisions at CMS. Okay, thank you. You can start.
So, good afternoon, everyone. My name is Alexander Wilinkin, and I'm going to give a talk on the recent results on diffractive and exclusive processes with heavy ion collisions at the CMS experiment. I'm going to present today three recent results by CMS. I will start with the measurement of diffraction and exclusive photoproduction in proton-lead collisions at 8 TeV, which help us to understand the high energy limit of QCD and can be useful for cosmic ray physics and Monte Carlo tuning. And then I will present two most recent results released by the collaboration only yesterday. So these are two particle correlations in inclusive UPC, proton-lead collisions at 8 TeV, which extend the search for collectivity in the small systems for the case of photon-proton interactions. And the last results I will talk today is exclusive digest production in ultra-peripheral lead-lead at 5 collisions, which is the first step to access novel features of gluon distributions. So I will begin with the first measurement of diffraction in proton-lead collisions at 8 TeV. In this analysis, we looked both for proton-lead and lead-proton data, and we selected minimum bias events that should have at least one 10 GeV tower in the hadronic forward calorimeter, in one of the hadronic forward calorimeters located in the region of pseudoepity between 3.0 and 5.2. And we looked at single diffractive events which have two distinct topologies that are pomeron-lead and pomeron-proton interactions, which are shown with these schematical plots. And we can see that both of them are characterized by large rapidity gaps, and we can distinguish one from another by requiring the hadronic forward activity on one of the side. And the main difference between these two events is that for the Pomeron-proton topology, we expect a strong contribution from the photoproduction events enhanced by the photon flux from the lead ion. So let me move to the analysis description. We looked at the rapidity gap distribution, for which we divided the central detector having pseudorapidities below 3.0 into 12 bins, and the bin in rapidity was considered to be empty. We have no tracks with the transfer momentum above 200 MeV, or the total energy of particle flow candidates in the central region should be below 6 GeV. And in the more forward region of between 2.5 and 3.0, we should have no neutral hadrons above 13 GeV threshold. And finally, the rapidity gap itself was defined as a distance from the edge of the central tracker and the first non-empty bin. The plot to the right shows the rapidity gap distribution for both of the topologies, Pomeron lead and Pomeron proton. And we see that the spectra falls rapidly for both of them from 0 to 2 by a factor of 50 and then flattens, which can be explained by the fact that the low rapidity gap values are dominated by non-diffractive events. We also show the predictions from EPOS and Hygiene Monte Carlo, which are found not to describe the data for the large values of rapidity gap. And finally, we can even enhance the sensitivity to diffractive events if we extend the rapidity gap from the central region to the hadronic forward calorimeter by 2 units in pseudorapidity. So we require that we have, in addition, no particles in this very forward region. And these plots show, again, the cross-section for two topologies, but this time already corrected by detector and acceptance effects. And for the Pomeron-proton topology, we see a huge difference between the data and Monte Carlo, which means the strong contribution from photoproduction events in this topology. So let me move on to the second results, that are the first measurement of two particle correlations in inclusive ultra-peripheral proton-lead collisions at 8 TeV. In this analysis, we compared the minimum bias sample, which required activity in both hadronic forward calorimeters above 3 GeV, with the UPC enhanced sample, which required activity only on this proton side in the hadronic forward calorimeter, with the lead ion remaining intact. And this was done in the similar way to the previous measurement, exploiting the rapidity gap selection I just described. And so, since we expect the events to be on one side of the detector, events were selected having the rapidity gap between 5.0 and 7.5. And the plot to the left shows a comparison of the track multiplicity for these two samples. And we can see that while for the minimum bias, it is more or less flat, we see a fast falling for the UPC enhanced sample, and it is limited by the number of tracks less than 35. Also, 3 areas highlighted show the bin limits which were used for the studies of two particle correlations. So the two particle correlations were studied in the region of the central tracker with a pseudorapidity below 2.4 and with a transfer momenta greater than 0.3 and 3.0 GeV, and the standard technique of calculating the two-dimensional correlations was implemented in this analysis. These plots show the two-dimensional correlation for the photo production and for the minimum bias events, and their projection for far from the jet fragmentation region. And this projection is then fitted with the Fourier fit with 3 components, and we see that both photo production and minimum bias distributions have significant first and second two-particle Fourier coefficients obtained from this fit. And next, the main systematic uncertainties obtained in this analysis comes from the rapidity gap selection by varying the size of the rapidity gap, the trigger efficiency, tracking inefficiency, and the primary vertex position, resulting in less than 8% for the first and 30% for the second Fourier harmonic, and they are showed with the gray boxes on the plots below. And these two plots show the UPC sample for 2 distinct PT regions. So the left plot shows the PT region starting from 0.3 GeV, while the right plot shows the region starting from 1.0 GeV with, and the V1, V2, and V3 are shown as a function of track multiplicity. For both of these regions, we see V1 being negative, V2 being positive, and V3 equal to 0, and we don't observe strong dependence as a function of track multiplicity. And finally, we extract the single particle azimuthal anisotropy Fourier coefficient V2 as a square root of the Fourier harmonic, and we compare it between the UPC and minimum bias samples, and we see that V2 is much larger in the UPC sample shown with the red points and increases with PT for both minimum bias and UPC data samples. And such behavior can be explained by the fact that V2 from inclusive UPC events seem to be strongly affected by jet-like correlations. So I came to my last results I want to present. That is the first measurement of exclusive jets in ultra-peripheral dead-lead collisions at 5 TeV. And ultra-peripheral dead-lead collisions are dominated by the process shown on this diagram, in which one of the ions emits a photon. And so exclusive jet photoproduction is the only known process directly sensitive to the Wigner and Husimi gluon distributions, which are believed to be the most fundamental gluon distributions. And by looking at azimuthal jet correlations, we can study elliptic gluons, which has non-trivial angular correlations inside the nuclei. So the magnitude of the spatial momentum anisotropy can be measured by the second Fourier harmonic, similar to the two-particle correlations, with the phi angle being the angle between the vectorial sum of two jets Qt and the vectorial difference Pt. So let me move to the analysis description. First of all, we selected events with at least one track in the central tracker, and we looked at particle flow jets using the anti-KT algorithm with the jet cone equal to 0.4. And since we look at exclusive dijet production, we selected events with only 2 dijets in the central region, and the leading jet having transfer momentum greater than 30 and subleading greater than 20 GeV. And we also suppressed non-exclusive background by weighting activity in the forward colorimeters, hadronic forward, hadronic end cap, and electromagnetic end cap above certain noise thresholds. In this analysis, we used the RAP-GAP Monte Carlo to model exclusive digest for the production, and this Monte Carlo has been extensively used by H1 and Zeus collaborations to model electron-proton collisions at HERA, and in our case, we tuned the photon flux to match the case of ultraperipheral LED collisions. And next, about the selections, we also exploited the repeating gap selection described above, but with the only difference that since we require Veta in the colorimeters, we calculated the repeating gap only from the tracks in the central tracker region of 2.5. And photon-LED interaction is a very asymmetric process in rapidity, so we defined two separate data sets, one of them having large backward rapidity gap and small forward rapidity gap, and vice versa, so we can know which of the LED ions emitted the photon. And thereafter, samples were merged by changing the rapidity sign of the jets in one of them. And finally, to further clean the sample from non-exclusive and two-photon processes, which are background, we require that we have no tracking activity far from the jets in the backward region, and we also required the rapidity, backward rapidity gap to be greater than 1.2. These two plots show these distributions compared between the data and Monte Carlo, and we can see that our cards effectively remove the residual non-exclusive background. Finally, these two plots show the basic digest kinematic, the digest invariant mass, and the digest rapidity, both for the data and reconstructed RAP-GAP Monte Carlo, and we see rather good agreement between them, which confirms that the photon flux in RAP-GAP Monte Carlo was correctly tuned for the case of ultraperipheral collisions. And these plots show the digest kinematic distributions of the PT and QT, which are the vectorial sum and the vectorial difference of the two jets, and the scatter plot. And finally, the measurement is performed in the PT greater than QT region, which is the back-to-back limit, and we limit the QT by 25 GeV as seen on this plot. And finally, we have more than 9,000 digest events passing all analysis selections. The main systematic uncertainties in this measurement come from jet energy scale and jet energy resolution effects, which are the dominant in this measurement. And we also, since we also measure the angular distribution, we also consider the jet angular resolution, and we have a small contribution from the purity of the sample and the trigger efficiency. So I came to the results of this measurement. These two plots show the dn over d phi distribution with the phi, the angle between qt and pt vectors, and we see it peaks around 0 and pi for both in data and Monte Carlo, with the peaks in Monte Carlo being more pronounced. And the plot to the right shows the second Fourier harmonic, or the average of the cosine to phi, as a function of qt. And we see that it reaches a constant value around 0.5 for qt greater than 10 GeV. And the similar trend is also observed in RAP-GAP Monte Carlo, but the RAP-GAP prediction is significantly higher than the data. And in this analysis, we performed two useful cross-checks. First of all, we looked at the toy Monte Carlo with back-to-back jets smeared with detected resolution effects. We also seen the peaks in the phi distribution around 0 and 3, but the second Fourier harmonic fastly reaches the value equal to 1. And we also performed the mixed event calculations that are known to have no physical correlations by mixing the leading jet from one event with subleading jet from other 5 randomly selected events. And we found the negative value of the second Fourier harmonic, which is expected for the case of no physical correlation. So let me show once again the main results of the second Fourier harmonic, and we see that the average cosine of 2 phi for the data is below the back-to-back expectation, which is equal to 1, and also below the prediction from the RAP-GAP Monte Carlo. So our data calls for theories to explain the observed QT dependence we have seen. So I came to my conclusions. I presented several nice recent results from the CMS collaboration. That are the first measurement of diffraction in proton-lead collisions at 8 TeV, in which we have seen strong contribution from photoproduction events to the Pomeron-proton topology. Next, I presented the first measurement of 2 particle correlations in inclusive ultraperipheral proton-lead collisions, which extended the studies of collectivity for the case of photon-proton interactions, and we observed non-zero V2 larger than in minimum bias events. So we expect a strong effect of jet-like correlations here. And finally, I presented the first measurement of azimuthal anisotropy from ultraperipheral dijets and lead-lead collisions at 5 TeV. And we observed the QT dependence of the second Fourier harmonic in the data that is not described by RAP-GAP Monte Carlo prediction or back-to-back dijets. And so it is the first and essential step to extract the gluon Wigner-Husimi distributions believed to be the most fundamental gluon distributions in nature. So thank you very much for your attention.
Thank you very much, Alexander, for your presentation, also for being just on time and presenting these new results. So let's see if we have some questions from the attenders. I don't see any raised hand, and no from the mattermost. So can you please put your summary slide, please? So you have this cross-section for proton-lead collisions, the diffraction cross-section, right?
Yeah.
What is the number?
You mean the microbarn?
Yes.
Yeah, it's microbarn.
Oh, yes. Okay, I can see. Any comparison with other experiments at LHC?
No, to my knowledge, this is the first measurement of diffraction in proton-lead collisions. So
in the whole LHC, right?
Yes.
Yes, yes.
Not only in CMS.
Very interesting. Okay, if there is no more questions, thank you very much, Alexander, for this talk. And now we go for the next presentation. Agnieszka, please. Agnieszka Tuszak. Okay. Agnieszka will give a presentation about coherent photoproduction of yesite in nucleus collisions in the color dipole approach. Okay, Agnieszka, you can start now. Thank you.
Okay, good afternoon. Can you hear me?
Yes, very well.
Okay, thank you. So my name is Agnieszka Łuszczak, and I would like to tell about coherent photoproduction of JPSI in nucleus collisions in the color dipole approach. And my outline is as follows. So first, I would like to tell a few words about motivation and formalism for nucleon and nuclear target. Then I would like to tell about dipole models. Then I will show predictions for JPSI production. And at the end, I will show results for photoproduction in ultraperipheral collisions and summary. So our motivation, this work was prepared in collaboration with Wolfgang Schaffer, and our motivation was the recent measurements from LHC for coherent exclusive production of vector mesons in ultraperipheral heavy ion collisions at the LHC. And the production takes place via the diffractive photoproduction process, where one of the ion serves as a source of quasi-real photons, and the second ion plays the role of the hadronic target on which the diffractive photoproduction proceeds. The exclusive production of vector mesons composed of heavy quarks like JPSI in heavy ion collisions has been investigated. The heavy quark mass provides, in these processes, the heavy quark mass provides a hard scale which ensures a dominant contribution from short distance, so that of course we can use perturbative QCD approach. The diffractive photoproduction becomes a sensitive probe of the gluon structure of the target. So as I mentioned at the beginning, in this analysis, we use the color dipole approach, which allows us to take into account nuclear effect once the dipole cross-section on free nucleon has been fixed. In a view of later applications to ultraperipheral heavy ion collisions, the Herrat energy range is the most relevant to us. And for the production of JPSI vector mesons at high enough energies, the coherent length, LC, we calculate as 2 omega divided by mass in square of vector meson. And this mass is much larger than the size of the proton. And omega is the photon energy. And in our analysis, and the JPSI production can be described as elastic scattering of CC bar pair, which has a R conserved during the interaction, and gamma CC bar transition and projection of CC pair on the bound state are encoded in the light cone wave functions, which depend also on the fraction Z of the photon light front momentum carried by the quark. Now, maybe I could skip, but so I put on my slide a formula for the coherent diffractive amplitude on the free nucleon, and this is a long formula, but what is important here that the X is equal Here, mass of the vector mesons in square divided by energy. So W is the proton center mass energy. Our amplitude is normalized such that the differential cross-section is obtained from this form, and the overlap of light front wave function of photon and the vector meson we can write as follows, as this formula. And now is formal is for dipole for nuclear targets. So for dipole cross section, we assume such a factorized form, and as the overlap of vector mesons and photon light conway function is obtained from gamma mean vertex, and is given by this formula. What is important that we in our investigations we will use dipole cross section with 3 different parametrizations. So now I would like to tell a few words about nuclear formalism. So, so for this processes for nuclear targets, color dipoles can be regarded as eigenstates of the interaction, and we can apply the standard rules of Glauber theory. So the Glauber form of the dipole scattering amplitude for LC for bigger, much larger than the nuclear size, then this is a coherence length, much larger than the nuclear size, we use the Glauber form, which is written here. And below you can see the dipole amplitude, which is expressed by this formula, and here is a dipole cross section, and this is a optical thickness calculated from a Wood-Saxon distribution, which is here. Okay. So now the diffractive amplitude in B space we also need, and just I know that I'm showing a lot of formula, but it's the last one. So there is the diffractive amplitude, and the nuclear form factor depends on the final longitudinal momentum transfer, QZ. And at the end, we obtain the total cross-section for gamma ion and vector nucleus ion reaction is finally obtained here. Okay, so as I mentioned, we use for this predictions and the production we use for nuclear targets, the dipole cross section. And now I would like to show you three parameterization which we use. So dipole picture of DIS is shown here. So photon fluctuates to quark anti-quark pair. R is the dipole size, Z is longitudinal momentum fraction of the quark anti-quark, and we can factorize this process as dipole formation and dipole interactions. And this dipole cross section is responsible for dipole interaction, and here you see cross section gamma proton. So for this collision, and here you see the formula for dipole proton interactions. And now I would like to show you three parameterization which we use for this dipole cross section. First is GBW parametrization with heavy quarks. So it is written like this formula. R as in square is saturation scale, and here we have 3 parameters, B0, X0, and lambda, which we can obtain, get from fits of this amplitude to F2 data. The next parametrization is BGK parametrization, and this is parametrization when Q square just describe the scale, like you can see here, of the gluon density, and mu0 in square is a starting scale, and gluon densities evolve according to the leading order on next to leading order DigiLab equation. And we can use 3 parametrization for a gluon. Here I show only 2, but it's also, we can use 3 with the negative gluon also. So here are with 3 parameters, and below is for 5 parameters. And we can also take a slightly different choice of this scale, which, and we use it in our analysis, which this interpolates smoothly between the C divided by R behavior for small r and the constant behavior. When mu in square is equal mu0 for r very, very big. Okay, and the last parametrization is IIM parametrization, which use a simplified version of the Balitsky-Kovchegov equation. The GBW and BGK models use for saturation, for the effects of saturation, the eikonal approximation. Here is a difference. This is Balitsky-Kovchegov equation, and here is a formula which we use for this parametrization. So we take the numerical values found in the XFITER code. I will tell a few words too about it. So my next slide is gluon density. This is a gluon density which was obtained from the fit with BGK parametrization, and this gluon density was used to the predictions for which I will show in next few slides. And I would like to tell you that all this dipole cross section and also gluon distribution was obtained by me using the XFITER software. And this is a project and unique open source QCD fit framework. And this code allows users to extract PDFs from a large variety of experimental data, allows access to impact review data, check the consistency of experimental data, and test different theoretical assumption. And in this code, I implement dipole models and the BGK parametrization. And I think it's worth to tell that LHC experiments provide the main developments and usage of the XFITER platform. And now it's around 30 active developers between experimentalists and theorists. Okay, so now I would like to tell about predictions of for JPSI production on the proton target. So for the GBW and IIM dipole cross-section, we calculate the total cross-section from this formula, and the diffractive slope was taken as this form. And for the BGK type of parametrizations, which proves to be more stable numerically, we substitute this Q gluon in the exponent. For gluons exchange in the amplitude carry different longitudinal momenta at small x. We have typically say that x1 is almost equal x, and x2 is much less than x1. And in such situation, corresponding correction, which multiplies the amplitude, is ICHEP factor. So you can see this correction, this factor here, and we add each to our analysis and to these dipole cross sections. Okay, and now I'm showing comparison with data. So these are predictions for drape side productions, and on the figure I'm showing total cross-section for the exclusive photo production as a function of gamma proton energy. And we observe that the range of 30 less W and, greater than W and less than 300 GeV. So here, almost here, the very description, the data are described well by all of dipole cross-section. Here you see this 3 dipole parametrization, 3 curves, red, blue, dash blue, and solid GBW with a new scale. The very high energy domain is covered by data extracted from the proton-proton proton-proton drape psi reaction by the LHCb, and here we didn't describe this data. Okay, now a few words about exclusive photo production in ultra-peripheral heavy ion collisions. So here, the left moving ion serves a photon source, and the right moving serves as a target. And the rapidity dependent cross-section for exclusive drape psi production from the Weizsäcker-Williams fluxes of quasi-real photons, we can write as follows. We use a standard form of Weizsäcker-Williams flux for the ion moving with a boost gamma, and omega is the photon energy written as follows. Okay, now I would like to show results for photo production in ultra-peripheral collisions. So on these two figures, I'm showing rapidity dependent cross-section for exclusive production of J psi in ion-ion collisions at per nucleon central mass system energy for the two energy 2.76 and 5.02 for ALICE CMS data, and on my right is for ALICE data. And my next My next picture is also rapidity-dependent cross-section for exclusive production of J-psi in lead-lead collisions at per nucleon center mass system energy for 5 TeV. And the last figure is the total cross-section for lead nucleus as a function of gamma ion center mass energy. Here we have 2 points. So our description is for this. Oh, okay. So 3 points is okay. Is quite good for this two, not for this one. And now I come to my summary. So we calculated the total elastic photoproduction of J-psi on the free nucleon and compared to the data available from fixed target experiments from the H1 and Zeus collaboration at HERA, as well as to the data extracted from proton-proton or proton-ion collisions by the LHCb and ALICE. We have applied our results to the exclusive J-psi production in heavy ion lead-lead collisions at energies equal to 0.76 GeV and 5.02. Description of published and preliminary data can be regarded well. It will be very interesting to investigate photoproduction in ultra-peripheral collisions at the electron-ion collider 2, where we will have a large Q-square. Thank you for your attention.
Thank you very much, Agnieszka. Very clear presentation. And
thank you.
Very interesting results.
Thank you.
Oh, these are new results, or you haven't published these calculations?
Yes, these results are published in last year.
There is a question from Daniel. Please, Daniel, can you?
Yeah, thank you. So thank you, Agnieszka. Very interesting result. So just a comment. I think it will be nice if you could also calculate the ratio between the what you have in your calculation in gamma A compared to gamma proton, so that we can see what effects are in the nucleus right case compared to the proton case. I think that will be very interesting.
Yes, I agree. Yeah.
So it's just a comment.
Thank you for a comment.
Okay, if there is no more questions, I will thank again Agnieszka, and please give us the opportunity to present the talk for Yaroslav Adam. Please, Yaroslav, are you there? Thank you, Agnieszka. Can you please stop sharing your screen?
Hi, thanks. This is Yaroslav. I'm here. Let me just share my slides.
Good.
Okay, you should see it by now.
Good. Yes. Yaroslav Adams from the STAR collaboration. Okay, please go ahead.
Okay, thank you. So thanks organizers for the opportunity to show results on the J-psi in ultra-peripheral collisions at REC. So the UPC collision, ultra-peripheral collision, is typically taking place at impact parameter greater than sum of nuclei radii, where we have electromagnetic fields of protons and ions as beam of quasi-real photons, which is proportional to z square. And we can study photoprotection in gamma P or gamma A. And also we have QED with gamma-gamma collisions. So actually we are using RIC as photon nucleus and photon-proton collider. So the field is described by Weizsäcker-Williams concept as and the field of relativistic charge makes the flux of equivalent photons which are incident on the target. So with Lorentz contraction and making a Fourier transform of the spectrum, we get the intensity as a function of photon energy, and assuming just a field of uniform relativistic charge, we see the flux of photons per unit area given by 2 Bessel function with the leading contribution of transversely polarized photons. And in terms of physics, we have the field to induce photon nucleus and photon-photon interactions, and experimentally we need large impact parameters to suppress short scale strong interactions. And in the end, we assume just vector meson or E plus E minus pair. Typically, the nuclei go out intact, but they can be excited by mutual Coulomb interactions, and they emit very forward neutrons. So experimentally, we are looking for events with just 2 tracks, maybe forward neutrons and nothing else. So with heavy mesons, there is advantage of perturbative QCD in a basic approximation. It's the two-gluon exchange, and we distinguish coherent coupling of the photon to entire nucleus and incoherent coupling to single nucleons in the nucleus. The momentum fraction of proto-gluons is given by photon nucleus center of mass energy, and at the leading order, the cross-section is proportional to square of gluon distribution of the target at the scale given by mass of the vector meson. And so the coherent cross-section is sensitive to nuclei effects to gluons at very low x. Actually, first data on GSI in UPCs at Collider were achieved by Phoenix. They measured GSI to E plus E minus with central tracking in drift chambers. They used identification in a Cherenkov detector and electromagnetic calorimeter, and they used 0-degree calorimeters for neutron detection. And they used forward beam counters to veto activity, which is not consistent with the UPC expectation. So the signal is shown on slide 7. So they measured pairs of E plus E minus with at least 1 neutron on either side of the experiment in a very forward direction and no other activity. And they demonstrated a very clear separation between the J-psi and QED background from gamma-gamma to E plus E minus. But these very first data had limited statistics to separate coherent and incoherent components in the J-psi. But it was this kind of proof of principle for electromagnetic studies at Hadron Collider, and it was very first measurement of exclusive J-psi in E plus E minus pairs. So now with the STAR experiment, we have central tracking and particle identification, forward counters, and neutron detection, where the main tracking part is time projection chamber at eta below 1, and time of flight to trigger on UPC events and identification and removal of out of time events in TPC. Then for trigger on the J-side to dielectrons, we use barrel electromagnetic calorimeters, and to veto non-UPC activity, we have beam counters, which are scintillators at eta from 2.1 to 5.2, and for very forward neutrons, we have 0-degree calorimeters for eta beyond 6.6. So to select the data for coherent J-psi in UPC at STAR, we aim for just 2 tracks and from meson at very low PZ, forward neutrons, and nothing else all around. So the rapidity acceptance of individual tracking gives overall acceptance less than 1, and the trigger aims for these two tracks and one neutron in each of these EDCs. Where at very low PT, which is signature of coherent production, we assume back-to-back electrons in B and C, some limited activity in time of flight, and showers in both ZDCs with energy deposition from 1 to 4 beam energy neutrons. In this region, the ZDCs are fully efficient to even single neutron, and we want veto from both beam counters here and here. Okay, now we can look in more detail to very forward neutrons from Coulombic excitation of nuclei. So when we take data from ZDs from 0-degree calorimeters on east and on the left from a west side of the experiment, we can do two-dimensional fit to both of these samples, showing peak of 1 neutron on both sides, side peaks of 1 neutron and 2 neutrons in either side, and also peak of 2 neutrons on both 0-degree calorimeters. And when shown in a projection to east and west side, we see clear description of the data on both sides of the detector. And so the neutrons are a convenient way to tag UPC events at trigger level. Now, looking at the mass of selected E plus E minus candidates, we see clear signal of the J psi, minimal like sign background, and we can describe it successfully by a combination of a crystal ball for the signal and empiric parameterization for gamma to E plus E minus, which effectively is a convolution of behavior of gamma cross-section and detector effects, mainly the trigger requirement on barrel electromagnetic calorimeter, which makes suppression at electron masses beyond 2 GeV. And so we use this mass fit to account for gamma contribution in the region of G psi signal. But to separate coherent and incoherent and gamma components, we need to use distribution of transverse momentum of J psi candidates, which is formed with electrons within J psi mass peak from 2.8 to 3.2 GeV. And it is convenient to make a decadic logarithm of PT square of the pairs, where we see clear separation between coherent J psi, incoherent J psi, and gamma to E plus E minus, where the coherent and gamma components are templates from Starlight, where gamma component is normalized using fit to mass distribution, illustrative normalization for a coherent part, and then we have fit to incoherent contribution, which is performed over incoherent region drawn in a solid part of the parameterization, and then is used in extrapolation to account for incoherent part over coherent signal. So with all these components now, we can calculate the coherent cross-section in bins of absolute T, where we put yield of coherent J psi at a given bin of T given by PT square of the J psi candidate. And we subtract gamma component using normalization from invariant mass, and we subtract incoherent component using results from fit to log PT square, and we divide it by acceptance and efficiency from Monte Carlo, and branching ratio and luminosity, and size of bins in T, and size of rapidity bin, which is just 2 for rapidity below 1. And we can then plot the J psi cross section as a function, as a function of T. And we have the data here, and we are comparing to Starlight based on vector domains in Galbert approach, and dipole models MS and CCK based on dipole approach. These two models were scaled to the case of neutron emission with Starlight to have proper normalization, given the trigger requirement was for arbitrary but non-zero number of neutrons on both sides. And so we see a sign of a defective dip around 0.02 GeV square, which is assumed to take place at this region by dipole models MS and CCK. And we see that the slope below this first defective minimum is consistent with starlight. Okay, next part is aimed for photo production of J-psi on polarized protons. So this is a proposal to measure generalized Python distributions, which depend on quark momentum and helicity in tensor space, and it's a probe to 3D imaging of the proton. And it appears that there is observable quantity as angular modulation to J-psi cross-section, and there is then calculation of the amount of modulation which we should observe with these GPDs, and with data by star with polarized protons and gold ions from 2015, we have proof of principle for such a measurement. And so looking at processes in polarized P gold, we can either have, depending on photon source and target, photo production on polarized proton, where we benefit from large photon flux for gold ions. And we can also have as a background process photo production on gold target, with photon originating from photon, and for this case we expect no asymmetry because the gold ions were not polarized. But given the intensity of the photons is proportional to electronic charge square, we we assume that photo production on protons is dominant over photo production on gold ions, and also over the process of gamma gamma to E plus E minus. And looking at UPC data from polarized P on gold, we see clear signal of the J-psi in mass of selected candidates, and we see in PT distribution expected shape with components of gamma P, gamma gold, and gamma gamma to E plus E minus. Where if we then restrict to the range in PT from 0.2 to 1.5 GeV, which is considered to study angular asymmetry, this in this region we have almost all events from gamma on polarized P. The purity is determined to be over 90%. And coming to results on angular on J-psi in gamma n with polarized protons and gold, we have the value of angular asymmetry at W gamma P of 23.8 GeV, where the result actually does not allow due to limited statistics to discriminate something about the prediction, but it's a proof of principle and tells that we can do this measurement, but we need more statistics and preferably at lower photon-proton energies. But it's very first measurement, and it's taken as a proof of principle for such kinds of measurements. Okay, so to summarize, we have collisions of light as a well-established experimental tool, and there is a large variety of processes to measure with future studies. Okay, thank you.
Thank you very much, Jaroslav. Quite a nice talk, an interesting topic. Let's see if there is some raised hand. Yes, Daniel, please.
Thank you. So, Jared, thank you. This is very interesting results. I just want to have a couple of questions. In for the first part of the analysis where you show the J-psi, all this analysis was done for XN? You say configuration where you have neutrons on both sides, at least one neutron on
yes,
both sides?
exactly. Yes, exactly. The trigger required at least one neutron in both sides, so it's all xn xn.
Okay, and do you have do you plan to make a similar analysis, but for other configurations like 0n, xn, or is
Yes,
there?
we have such study ongoing from data taken after 2014. We have also data on more combinations on ZDC requirements. So yes, it is ongoing study.
No, the other question is if there's what is the for the T distribution? You said that there is still not perfect agreement. There seems to be all the contributions in the data. Do you know what was the cause of this?
Yes, I had long discussions about this, and there is enhancement at larger T because of requirement for the neutrons, which makes change in the photon spectrum, which contribute to J psi. And also we are now working towards publishing refined results which use unfolding technique, which take care of migrations between different bins, and I can say it's much then the pattern is much more clearer than now.
Okay, that's good. And for the neutrons, so we have this noon Monte Carlo that you can correct neutrons efficiencies. But okay, I don't want to take so much time. Thank you.
Thank you.
Thank you, Daniel. Let's see if we have one more question from the participants. It seems like not in the chat, not in the raising hands, and no in the Mattermost. Okay, thank you very much, Jaroslav.
Okay, thank
Thanks
you.
for your contribution, and we pass to the next talk. Valerie?
Yeah. Hello. I will share a screen.
Yes, please.
Just a minute. This one. Share, and I will put it into presentation.
Okay, so now we have the last talk from this heavy ion session, the last one, and it will be Valerie Wozniakow for the collaboration. Okay, Valerie, please go ahead.
Okay, so I present recent results on vector meson photo production obtained by Alice collaboration with the data collected during LHC run-2 period. Actually, talk start from the introduction to the physics of ultraperipheral collisions and short reminding of the result obtained by Alice collaboration with previous round 1 data. Then I will show new results on coherent rho 0 photo production and forward rapidity J psi photo production in LED UPC at square root of S around 5 TeV in comparison with several several models, which includes saturation and gluon shading at small x. Then J psi photo production and proton LED collisions is presented, and after that preliminary result on ongoing analysis I will show you. So the electromagnetic field of fast charged particle described as a flux of quasi-real photons, whose intensity is proportional to its squared electric charge, provides copious photonuclear interaction in case of flat ions circulating in the LHC. In fact, the LHC becomes a source of huge photon flux when it works in a heavy ion mode. And if the impact parameter of colliding ions is larger than the sum of their radii, photon-induced processes dominate the interaction rate of your so-called ultra-peripheral collisions, which can be either two-photon process or photon nuclear scattering via Pomeron exchange coherently of whole nucleus or incoherently. And experimentally, there is a clean tool to distinguish between them vector meson transverse momentum. Another feature of UPC is that the collisions can be accompanied by a neutron coming from electromagnetic excitation of an ion. So my talk addresses to a question: is there gluon shadowing in nuclei, and how strong it can be? So the process looks like the following. Photon fluctuates into a bound cucumber system. In our case, it's CC bar, if we speak about GPSI, which is then elastically scattered off nuclei via Pomeron exchange, that is via double gluon exchange. The cross-section of GPSI photoproduction calculating in the leading order strongly depend on nuclear gluon distributions and the possible shadowing component of nuclear gluon modification. Alice's collaboration published first LHC paper on GPSI production in lead UPC at square root of S 2.76 TeV. GPSIs were identified via the muon decays in the forward direction, or the electron in barrel domain. The results are compared to theoretical models for coherent GPSI production as you can see, the data prefer the models which include nuclear gluon shadowing at moderate level, so at middle level. Coherent Psi2S for the production cross-section in UPC lead collisions was also measured in d-lepton channel or d-pion and GPSI decay modes. And you can see the same comparison with different models, and Psi2 prime Psi2S results confirm the results obtained with GPSI. So the main conclusion is that the model where all nucleons involved in the scattering, so impulse approximation with no shadowing, is definitely cancelled by our measurement. So Alice's setup was equipped by a diffractive detector in the period between run 1 and run 2, which is very helpful for UPC studies. It's a small sensorizer detector. UPC measurements rely upon a part of Alice setup, which includes muon spectrometer to reconstruct muons at forward GPSI rapidity, and inner tracking system and TPC to detect a charged particle in barrel. Also very important for UPC study, very important trigger and detectors. In our case, they are inner tracker system silicon pixel detector, sensolators with 0 and at, and TOF and muon trigger chambers shown on this plot. 0-degree calorimeter was used to detect neutrons from nucleus electromagnetic dissociation. Alice uses dedicated trigger chains with V0 and at detectors used in so-called veto mode, preventing events with other produced charged particles. That is, they effectively suppress background events. This slide presents visualization of recorded events where the main features of UPC event topology is clearly seen. Namely, one needs to find events with two unlike sign particles detected either in muon spectrometer or in ITS and TPC. And these particles should have so-called back-to-back topology in the transverse plane with a balance up to 1 GeV in order to keep incoherent events as well. So recently, Alice published measurement of ρ0 photo production at the square root of S at equal 5 TeV. Mass spectrum of detected two particles with well-balanced PT below 200 MeV, corrected on acceptance and efficiency, was fitted by a few component model, which includes Braid-Wigner for resonance, and interference between this resonance shape and direct d-pion production as well. So this plot, this picture shows the cross-section of for the coherent photo production of ρ0 in LED UPC as a function of rapidity together with the various model expectations enumerated here. And you see where they are described. It seems that the lower limit of this model, Guzey, Krushan, Zhalov, gives a good description, the best description of the data. And the model uses vector dominance approach and a Gribov-Glauber approach for gluon shadowing, starlight, and CCKT models are a bit far from data within actually 2 sigmas of experimental uncertainties. As I already mentioned, quite often UPC event is accompanied by a neutron coming from electromagnetic excitation of ion. Such excitation occurs due to additional exchange, photon exchange between ions. And Alice has a detector, a 0-degree calorimeter, intended to detect such forward neutrons, actually zero-degree neutrons. Moreover, ZDC provides a possibility to distinguish between a bunch-bunch crossing event and a beam gas event. And the detector has energy resolution enough to separate 1 to 3 neutrons, as you can see on the plot. And the scatter plot illustrates the data collected by 2 arms of ZDC. Based on the DC signal, it's possible to split whole sample into 3 subsamples with different signature in the DC. 0, 0, and without neutrons, 0n xn and xn 0 and with neutron detected in one arm of ZDC, and xn xn with the neutrons in both arms. Cross sections for coherent ρ0 photo production and LED was measured as a function of rapidity again, and in comparison with models described on previous slide. Overall description of the data by models means that a method to obtain the individual photonuclear contributions by using the forward neutron classes may be applied to the data, especially when the uncertainty in the measurement are reduced and the spread on theoretical prediction is better understood. So also the 2 charged particle data were studied in the mass domain far away from light meson masses. And this plot illustrates pair PT distribution for the mass domain above 1.6 GeV, where a clear signal of UPC is well seen, and mass spectrum for this domain shown on right plot, and the fit was actually, it's well seen that the data exhibit presence of resonance-like structure. And the fit was done in the same form as it was done by star collaboration, and obtained value for the mass and width of this resonance shape are shown, and actually several candidates listed in PDG can be for this shape. So Alice also published GPSI photo production measurement for both run 1 several years ago and run 2 just a few months or 1 year ago. This plot illustrates pair PT for the mass domain. This is the run2 data were collected for much larger integrated luminosity and under much more efficient trigger conditions. These bus facts provide much more statistic of analyzed sample for run2 data. You can see the comparison with run1. And the muon sample contains several physics channel, as it's seen on transverse momentum plot. They are coherent and incoherent photo production for both GPSI and Psi prime. Non-resonant muon pair produced in gamma-gamma, and incoherent production with a proton dissociation. The selection of D muons with transverse momentum below 250 MeV allows us to suppress most of incoherently produced muons. If we look at this part of the spectra, and D muon mass spectra is then fitted by crystal ball distribution for GPSI and a smooth polynomial distribution for gamma-gamma continuum. And the number of reconstructed GPSI is around 20 to 1,000 events. Measured cross-section of GPSI photo production at forward rapidities from -4 up to -2.6 is shown here, together with many theoretical expectations. Generally speaking, a lower calculated cross-section corresponds to stronger gluon shading assumed within the calculation. Calculation carried out under condition that there are no nuclear effects, so again, impulse approximation, clearly disagrees with the data and as a strong shading as well. So experimental data prefer calculation with a moderate gluon shading inside a heavy ion. The next topic of UPC physics I would like to present is a result in proton-lead collisions. In this case, a source of photons, actually ion, is known with high accuracy, and background coming from continuum D muon production is very small. Run1 data collected at square root of S around 5 TeV correspond to rather large gamma proton mass up to 700 GeV, and Bjorken X on the level of 10 to -5. And it's remarkable to mention that different classes of the data, electron, proton, proton, and proton nuclear, are consistent each other. The run2 data increase statistic of recorded events by a factor 5, and proton mass becomes behind 1 TeV, which correspond to X value, Bjorken X value close to 10 to -5. So this job is in progress. This slide presents preliminary result for the study, which are in progress now. They are analysis of events detected at mid-rapidity domain. GPSI photo production data sample contains sizable statistic of the events to provide actually precise measurements. The data samples of P2S and proton-antiproton GPSI decays have much less events. Nevertheless, this sample can provide visible measurement. So in summary, ALICE learned lead-lead and proton-lead UPC, which provides info for initial state of ion and dynamics of gamma-ion interaction. The photo production of ρ0 and at mid-rapidity and GPSI at forward rapidity were studied, and coherent cross-section were measurement and compared with available models. Also, resonance-like structure was observed at mass around 1.7 GeV. And also we have several studies which are underway now, and the news will come soon. And also we made some calculation for run 3 and run 4 expectation for lead-lead with ALICE collaboration, and we expect to collect I would say, a huge amount of GPSI candidates decayed into muons. That's all. Thank you.
Oh, thank you very much, Valerie, for this presentation and also for being on time. And let's see if there is a question from the attenders. Not in the chat, not raising hands, and no from the Mattermost.
So can I ask you, sorry,
yes,
can I ask a question?
Yeah, yes.
Yeah, thank you. In page 12 of your presentation, Valerie, thank you, it was very nice results. This is for 4 pions, so
Yes.
what is it? Okay.
Yeah. Pardon, I forgot to mention it's the pion decay. So we measured ρ0, and then we had a look at high mass.
Okay, but you require that the both pairs are within the raw mass?
No. We learned raw, and then we looked what's going on behind 1.6.
Okay, so it's pi plus pi minus.
Yes, exactly. Pi plus pi minus in this mass domain, 1.6, 1.9 GeV in between.
Okay. Now another question. In the round 1 data from ALICE, there is a nice plot for raw. You know, like I'm looking at page 11. So there is a nice plot that shows how the raw cross section depends as a function of the energy of the gamma LED system. And when you study in this analysis, you have effectively exploring different gamma LED energies. Do you have, or you plan to have like a plot that shows the energy dependence, how this neutron configuration changes the energy dependence of the raw studies?
Yeah, I see. Actually, I would say that we cannot promise to learn this in nearest future, because you can imagine that most of us have the same problem of manpower, and we have several analyses which are in a good shape. So we plan to finalize them at the beginning, and then perhaps we will return to this study RO0 from the point of view of what you said, how different ZDC configuration changes the picture. But it's not a first priority job. Unfortunately, we have to choose what to analyze at first priority.
Okay, thank you.
Okay, if there is no more question to Valerie, so we want to thank all the speakers. We have received this day 11 presentations, very nice, all of them, and very important for our field. Thank you very much to all, and see you tomorrow. Thank you.
Thank you.